Morning session, and our first, let me introduce you our first speaker, Professor Sergei Kukshin, and he will talk about small amplitude solutions for nonlinear beam equation. Please.
Okay, well, first of all, I'm very glad to talk at this conference. This is the seventh conference on the differential and functional differential equations. So I'm very glad that the conference lasts because it clearly became an important event in the mathematical life in Moscow, especially for analysis in Moscow. And I think this is the fourth time when I talk at this conference. So what I will talk about? So you see, so now for modern mathematics, one of exciting, popular, and very complicated topics is the business of study of small amplitude solutions in nonlinear partial differential equations. Well, why small amplitude? Well, okay, why nonlinear Hamiltonian PDEs? Nonlinear, there should be Hamiltonian PDEs. Why nonlinear Hamiltonian PDEs? Because they're very important for physics. Because many the most relevant physical PDEs they're Hamiltonian PDEs. Why small amplitude solution for Hamiltonian PDEs? Because for the modern stage of development, we have absolutely no chances to understand what happens with large solutions for equations like this. Right, and so just to explain what are the problems here and what, for example, right now people are trying to do, let us start with maybe the most famous example. Let's consider nonlinear Schrödinger equation. Right? And here there is a big difference. If you consider nonlinear Hamiltonian PDE, either in the whole space or in some bounded part of the space. That is to say, either in infinite volume or in finite volume. I will always, and because qualitatively and quantitatively and from the point of view of techniques, these two cases are very different. I will always talk only about finite volume, and I will restrict myself to the periodic boundary conditions. So always space variable will belong to the torus of dimension d of period 2pi, right? And this is one of the most famous nonlinear Hamiltonian PDE. And look at this. So this is g is a real analytic function, real valued, right? And I just assume that the function as a function of v equals to v plus the perturbation for the v squared. And as I said, I wish to study small amplitude solutions for this equation. And I wish to study behavior of small amplitude solutions for this equation for large values of time. This is very complicated. And one way to see why it is really complicated, just simply because now, if dimension d is bigger than 3, we cannot prove that even for smooth, small initial data, solution is forever, right? So I'm going to study an object such that in general we even do not know that this object exists, right? So this definitely cannot be easy. Right, okay, but since I'm going to study small amplitude solutions for this equation, then clearly they are related with the linearization of this equation at 0. Linearization of this equation of 0 is one of the most famous and one of the most important linear Hamiltonian partial differential equations. This is linear Schrödinger equation. And just of course, as just everybody knows, this is a perfect example where we can write any solution for this equation using the Fourier method. Let me make a copy of this formula on the blackboard. I will refer to it. So any solution can be written down of linear equation, can be written down as a linear combination of the Fourier mode. So Fourier coefficient us times exponent of lambda s, where lambda s is a frequency number s, times exponent isx. Why exponent of isx? Simply because this is a eigenfunction of the linear operator, which is the Laplacian operator now, and lambda s frequency now equals to norm s squared. If we replace this linear Hamiltonian PDE by some another Hamiltonian PDE, for example, like wave equation, like beam equation, like Rother-Wegener-Friis equation, then essentially what will change? that the frequency lambda s will change. Lambda s will change. And the function which maps s to function lambda s as a function of s is called distortion relation, and it is extremely important for the theory both of linear Hamiltonian equation and for nonlinear Hamiltonian equation, right? And then so what we want to understand how this solution of linear equation will perturb in the nonlinear equation. So can we prove that in some reasonable way this equation has a close for this solution for linear equation? There is a solution of nonlinear equation which is close to this equation forever in some sense. And this is very complicated because, as I said, for higher dimensions, for dimension bigger than 3, we even do not know that the solution with such initial data for the nonlinear equation exists forever, right? So this cannot be easy task to do. Okay, so these solutions, they're just almost periodic functions of time t. If somebody does not know definition of almost periodic function, it doesn't matter. And this is what I'm talking about. This is a dynamical system approach. So I will regard this solution as an almost periodic curves in the space of functions. You see this, right? So just for me, MLS, this is an ordinary differential equation in the space of functions. Solutions for this equation are curves in the space of functions. So linear solution like this, they're just almost periodic curves in the space of function. This is really this is complicated, and situation becomes a bit easier if we consider special case of solutions like this. This is the case when we consider linear solutions for the linear equation, when just only finitely many frequencies are excited. So just what I'm doing. So here index S belongs to the whole lattice ZD, because for me D will be space dimension always. But let us consider the case when only finitely many modes are excited, right? So that is to say, I'm doing the following. I consider a finite subset of the D lattice. I will denote the number of these points of this lattice n. It will be n forever. And I consider solutions where only modes from the final subsets is excited. This is literally the same, but now I have only finitely many summands, right? And now, okay, right. So this is yes, and I need some name for the set A, which is important for me. I will call it the set of linear excited modes, right? Because for the solution of linear problem, only modes like this are excited. If I wish to study related solutions of nonlinear problems, of course all modes will be excited because of nonlinearity, but still these modes will be excited more than other modes. And just in this case we have only finitely many frequencies which are involved in this formula, right? And so they say that they just solutions like this define quasi-periodic curves in the space of functions. Note that this solution UA can be written like this. And now Fourier coefficient number S equals the original Fourier coefficient times this object. This object is a complex number of modulus 1, right? Therefore, if I consider the quantity, which is called in physics and in symplectic theory, the action number S, and by definition, the action number S is norm of Fourier coefficient number S squared divided by 2. This is rho S action number S, right? Then these solutions are such that the first all actions stay constant as a function of time, right? They're just time-independent quantity. This is why they're called actions. And for quasi-periodic solutions, only finitely many of these actions are non-zero, and the rest are zero, right? So this is what we have here. And these are quasi-periodic solutions. Well, just let us denote this vector formed by the non-trivial actions. Let us denote this as vector rho.
This is the vector of the amplitudes or vector of the actions of solutions. So why I call them here amplitudes? Because sometimes people call actions amplitude. It is not. It's an ambiguity. So it would be better to say here actions. Then just look what happens. Look what happens. Let us consider collection of functions such that for this function Fourier coefficient number s such that the corresponding action equals to exactly rho s, right? Then if you look backward at this solution, we will see that our solution always stay in this set, And also we say immediately this this set is nothing but n-dimensional torus embedded in the space of functions. Why it is n-dimensional torus? Because I have n non-trivial Fourier coefficients, and Fourier coefficient number s, it's a complex number with just fixed radius, with a fixed length, right? So Fourier coefficient number s varies along a circle, and we have n Fourier coefficients. So the total collection of functions like this is a direct product of n copies of circles. So this is a torus of dimension n, right? And so in this language, we have a general problem number one. Study how small amplitude almost periodic solutions of linear equation Schrödinger are perturbed in the nonlinear equation, and how this happened for all t. This problem is hopelessly complicated. So this is really hopelessly, because simply we have no idea what really happens there, what really happens with the solutions like this. You see, this problem is very complicated because physicists do not know answer to this problem. Physicists do not have a real understanding of what happens with a solution like this. They would say that some mixing happens there, but which mixing, which kind of mixing, how it happens there, then just nobody knows. But when we study quasi-periodic solutions like this, right? And if we restrict, yes, and please, of course, questions are welcome. So then just, you see, so I'm trying to avoid heavy formulas, so just please ask questions at any moment. So you see, if you study what happens with quasi-periodic solutions like this, right? Then to answer this question, becomes feasible, becomes doable. At least if we restrict our question a bit to the sub-question, what happens under perturbation in the perturbed equation with typical quasi-periodic solutions like this, right? Of course, one should explain what does it mean typical, but then this problem is feasible, this problem is doable, and this is precisely the problem which is being addressed by the theory Km for PDEs, right? So, so just everybody knows, of course, here that the Km theory was created in just early 50s in pioneer work by Andrei Nikolaevich Kolmogorov, when just detailed were filled later mostly by Vladimir Ilyich Arnold and Yuri Moser, and in late 80s Km theory was applied to nonlinear partial differential equations. This is and so the Km for PDE appeared, but then for long all applications for the Km for PDEs, they were restricted to the case when our partial differential equations to which we apply the theory is only one special variable, right? And for example, the equation number 2 for the analysis equation is what it was treated in rather big generality. So very, I think, good and sufficiently good answer to the question number 2. What happens to solutions like this under perturbation in the nonlinear equation? So the answer was found in my paper with Jürgen Perschel. So it was long ago, as you see. But if we consider the same question, but in higher dimension, when a dimension is bigger than 1, then the complexity of the problem changes dramatically. And if we keep asking the same question, let us take a quasi-periodic solution of linear Schrödinger equation like this, and let us ask ourselves what happens when we try to perturb it to a solution of non-linear Schrödinger equation. then we will find difficulties which are hopeless for today. Because what really happens here, that to apply usual KM ideology to this question and to understand what happens to this problem, to these problems under perturbation, one has to check a number of extremely complicated nonlinear non-degenerate relations. Look, you see what happens here. When you apply to the KM ideology to the question I'm talking about, to the dimension bigger than 1, we start to construct nonlinear objects. And after a number of nonlinear steps, we just arrive at a collection of nonlinear functions, which are the functions of Fourier coefficients. And then we must check that no one of these functions vanish identically. And this turned out to be really transcendently complicated problem. So this problem was addressed very recently by the Claudio Processi and Michele Processi. So it's an interesting couple because Claudio is the father of Michele, and Claudio is one of leading experts in algebraical geometry. So you see the all heavy, but really leading. So he's really first-class algebraical geometrist. And heavy tools and heavy methods of algebraical geometry were just applied to this business of non-degeneracy relation. But the result is conditional. The result is conditional that we can tell what happens with these solutions, provided that non-degeneracy relation holds. But there are absolutely no way to check if this non-degeneracy relation are valid or not. And even unfortunately, as we understood now, in some situations we know that they fail this non-degeneracy relation. You see, so this is one of these cases. Of course, we can start to take any solution like this, take very good computer problem, and then we can start to say about computer assisted proof. But this sounds in a way which just nobody is really happy with. And if you Google the name Claudio Processi, Michele Processi, you will find the publication. You can just see what really happens there. And the same problem will appear if you talk about small amplitude solutions of other nonlinear Hamiltonian partial differential equations. Wave equation, I don't know, just any equation which just exists in high dimension. So in this my talk, I will present a way how to handle this difficulty, which is suggested in my joint work with Håkan Eliasson and Benoit Gerber. So our idea was the following. You see, let us consider the case when the non-linear partial differential equation, which we talk about, naturally contains a parameter. In typical case, it's a mass parameter. So let us consider the case when this is a non-linear partial differential equation, which describes what happens with a non-linear particle of mass m, right? And this is more or less what we felt on the wall. I will give all the references. There should be ways not from algebraical geometry, but rather from analysis and from a rather naive theory of analytical function, to prove almost for free that for most values of the mass parameter, this non-degeneracy relation which stops Processi and Processi, they fulfilled. But not for the reason for algebraical geometry, because algebraical geometry equations are very complicated, but for the reasons of analysis. Something like the set of zeros of an analytical function have zero mesh, like this, right? And then this is what we started to think about. And the main example for us was one of really the most important nonlinear Hamiltonian partial differential equation, which is a Klein-Gordon equation, right? So you see here m is the mass of particle, and this is very natural mass parameter. And this is what we started to think about. But unfortunately, we failed here, and the problem which stopped us when we started to work with this equation was that unfortunately here the distortion relation, frequency lambda s, which here is norm s squared. Here this is square root of norm squared plus m. And this is for the purposes of KM theory, this turned out to be much more complicated. Why? Because square root of norm squared plus m equals to norm of vector s plus a small perturbation. Now look, if dimension equals to 1, norm of vector s is an integer number. Everything is fine. In dimension 1 we can do the job. But if dimension is bigger than 2, norm length of integer vector is the square root of integer number. It's a square root of integer number. And Differential properties of square roots of integer numbers, they're really complicated. They're really complicated. So again, lot of technical issues are here, which we did not overcome. For a moment, I will discuss this at the very end of my talk. You will see, okay, so we had a dichotomy here, either to fight with this problem, which is not hopeless by the way, or just to consider something easier and just to see the way through, to understand what happens here, use an equation easier than this equation. And this is what we have chosen. So we have chosen to consider, instead to fight really heavy fight with this equation, consider easy equation. Easy equation, this is a beam equation. This is a beam equation, so it is of some importance, at least in dimension 2 for the mechanics of solids, but for us this is a good model for the nonlinear Klein-Gordon equation, which is extremely important for physics. You see, so this is the same equation, but instead of Laplace I have Laplacian squared. What is the main technical advantage for this equation? That now frequency lambda s is given by this relation, and now watch, now lambda s equals to norm s squared plus something plus a small perturbation. But norm s squared is an integer number. Differential properties of integer numbers, of course, they are well, just for the purposes of at least of our studies, they're just almost obvious. And this is the main advantage which we got when we have chosen this equation. Okay, so this equation was considered earlier, for example, by our colleagues from Nanjing, Genk and Yu, and the preliminary transformation, which reduce this equation, formal transformation, so just non-local transformation, which reduce this equation to equation very similar to nonlinear Schrödinger equation by beta. This we borrowed it from their practice. So look, and then I want to briefly present the scheme, how one can treat this equation, and what is it, and what and what is a possible approach to study small solution for this equation. Well, first come preliminary transformation. Let's consider operator lambda, which is a square root of Laplacian squared plus m. And let us make the following substitution. And this is substitution which is well known for physics, for the theory of Klein-Gordon equation. I believe that it even can be found in the book of Reed-Simon. If not, then just definitely in some papers of Barry Simon, for example. So, but this is a version of this physical substitution for the beam equation. So you see, let us consider new function, which is a linear combination of u and u dot. Everybody understands that it is then to work with this equation, it's a good idea to consider it to replace second order equation as a system of two first order equations. So introduce as a new variable du over dt. But it turned out that even a better idea to consider new variable, which is a complex linear combination of u and du over dt, right? And then easy calculation shows that this function of psi satisfies this equation, which is very similar to NLS. You see this? So psi dot equals I times lambda applies to psi, and lambda is very much like Laplacian, you see this, right? Plus a nonlinear perturbation. Nonlinear perturbation, this is something which corresponds to this essentially cubic nonlinearity, and this nonlinear perturbation is given by this explicit formula. I take this function g of x u, but I should have to substitute here instead of u this object, right? And I have to apply the operator lambda to -1 afterwards. And this is really very similar to the NLS equation, because this is a nonlinear Hamiltonian equation. It can be written in the following form. Of course, now psi is a complex function of dx, right? So instead of having second order equation for one real function, now I have a first order equation for a complex function, right? So this is like a system of two first order nonlinear equations. It's technically better. It's only technical difference, right? So this is equation which can be written in the following form. I take a Hamiltonian. Look at this Hamiltonian. I have a quadratic path, which is usual quadratic path, plus some nonlinearity, when the nonlinearity function G capital is simply integral of function G small, and then the beam equation can be written like this: psi dot equals to I times gradient of the Hamiltonian H, right? So this is technical advantage. So this really shows that this is something similar to the NLS equation. Let us try to understand what can we do with this equation. Well, okay, so let us do what physicists always do and what just everybody does. Let us decompose this complex function psi which we have here just in Fourier series as we did with just NLS equation, right? So this is Fourier series, Fourier coefficient number s is psi s. Let us also consider complex conjugated function, right? So this is complex conjugated function. And now you see, now there is this also technical trick which was known for everybody. So this is technically advantageous to consider, okay, and just solution psi of x is a real solution which give rise to a real solution of beam equation, provided that really these two functions are complexly conjugated. But it turned out that technically this advantage just to consider more general case when the second function is not necessarily complexly conjugated to this one, and to consider psi s and psi s bar as just independent variables. And to do this, we denote psi s bar as a new variable eta s, right? Then the complex conjugated function has the following form, and then it is calculation. Then we can write down the nonlinear beam equation, which was this Hamiltonian equation, as this equation for the psi and for psi conjugate. You see, for the real solution, this is the same equation. So if I apply bar to this equation, I will get this equation. But again, so it is technically advantageous. Technically advantageous to forget that eta s equals to psi s bar and consider this as a system of higher dimension. And again, you see, so it's a Hamiltonian system. And the Hamiltonian now is like this, right? So well, just we have here this vector of psi Fourier coefficient, which is a vector psi for me. I have here this vector of eta Fourier coefficient, which is a vector eta for me, and the reality condition is that eta equals to psi bar, but I will consider also solution which are not real. At the very end, I have to check that my theory applies to the real solution, but it does. And I recall that the function g here, this is something like u to the degree 4 plus higher order terms. And then, okay, then just what can we do with this equation? As before, we fix the set of linear excited modes, right? So these are solutions of the linearized equation, and the linearized equation, of course, this is the equation which corresponds to this quadratic Hamiltonian. So it is really very much like linear Schrödinger equation. And I want to understand what happens to the solutions to these solutions of linear equation when I switch in the nonlinear dynamics. So the set of excited modes, this is some finite set in ZD. It contains n points. I will denote complement as L, and just in this picture, the set A contains only 2 points, right? But the theory is rich and non-trivial even if the set at A contains 1 point. So you see, even if n equals 1, what I'm talking about is new. Okay, so A is a set of excited modes, L is complement. I consider the vector of small amplitudes. This is the amplitudes of the unperturbed solution, right? And okay, so then this n-dimensional torus on which this solution lives. This we can see that now this n-dimensional torus using the complex coordinate can be written like this. So lower Fourier modes, psi A, eta A, which corresponds to this linearly excited modes, they are complex conjugated because I want to stay in the vicinity of real solution, and then the actions, first n actions, they are equals to rho A, which is some given vector, and the higher actions are 0. So this is n-dimensional torus on the functional space, which is invariant for the linear equation. And I want to understand how non-linear equation behaves in the vicinity of the stores, Right? So my goal is to study solutions of the non-linear beam equation near the stores. And I remind that this torus is invariant for the linear beam equation, and the quasi-periodic solutions like this of the linear beam equation, they wind in a quasi-periodic way, which is usual for KM series around the stores. Question: what happens with beam equation in the vicinity of this invariant torus for the linear equation? Okay, so what is the main abstraction here? What is the main difficulty here if you start to use KM machine, which quite a number of people here know very well, because here there are at least two really deep experts in the KM theory. So just once again, I have a finite set of linearly excited modes, and now for the first time I have to impose one restriction. Do I have to impose some restriction on the set A? And the answer is yes, I must impose some restriction, but rather mild restriction. I will say that the set of excited mode is admissible if any 2 points on the set A are such that their lengths are different. For example, in this picture, of course, the set is admissible because here length is 2, and then this length is root of 2, right? And now easy lemma that says that admissible sets are typical. What does it mean? If in the lattice ZT, I consider the cube of size n capital, and if I at random throw n small points into this cube of size n, right, then the probability that the obtained set is admissible is like this. It becomes close to 1 if the size of this a priori cube is big. Right? Okay, so this is not a heavy restriction. This is rather mild restriction. And by the way, what happens if I violate this restriction? Something much more complicated. Okay, then as I said, the frequency of the linearized equation are numbers like this. You see, frequency number A is close to norm A squared, that you see, and it explains how it looks. Now look, this formula shows that the frequency lambda s, which corresponds to the frequencies s from the finite set, they are the most important for us. Because these are, on the language of the KM series, this is precisely the set of frequencies of the amplitude of the periodic motions. Let us denote this finite set of main frequencies as omega. This is the set of main frequencies. Okay, so now the KM machine, it is an iterative procedure. It is an iterative procedure, and formally this iterative procedure, and this was well known to Poincaré, well known to everybody long ago. It works perfectly well, if not formally, if not for the fact that when we run this iterative machine, then in our construction we just occur divisors which never vanish, but which can be very, very small. You see, the problem with KM procedure is that we have divisors in the formulas which can be very small. And for the equations like this, these divisors, they always are of the following form. You see, I take a frequency vector. I take a frequency vector like this, which corresponds to the most important n modes. I consider linear combination of frequency vector like this, and I add some constant. And depending on the complexity of the KM theory, this constant is either integer or is a real number. For us, it should be real number. You see, so our problem are that we have to divide from time to time on numbers like this. And if this number is very small, then just we are in serious problem. And okay, and this sets a bar here. The KM machine, and again, just many people here know this very well, the KM machine works in such a way that the set A bar is either the original set A, or the set A plus 1 point, or the set A plus 2 points, right? So the whole problem of the KM theory is because of linear combination like this can be very, very small. But then a very nice result was very nice result was found by Jean Bourgain something like 20 years ago, and this 15, and it was developed to a very powerful, beautiful lemma by Dario von Buzin just something like 5 or 10 years ago. This result is like this, you see. So let us remember now that everything depends on the mass parameter. It's what I started with. That mass parameter, this is what give me possibility just to attack this problem, right? So this resonant relation, this possible small divisor, also depends on the mass parameter. And it turned out that the sets of mass parameter where this linear combination, where this possible divisor can be very small, you see, it admits absolutely explicit estimate from above. Absolutely explicit estimate from above. This is remarkable formula. And this formula shows us that if we throw away some small set of mass parameter, then our divisors never will be really extremely small. This is a good hint why the KM machine can work. This lemma applies as well to the nonlinear Klein-Gordon equation, but there for the moment it is not sufficient for us just to go to the end. But this is key lemma. You see, just throwing away some small set of mass parameter, I guarantee that all divisors which occur in my construction, they never will be extremely small. Right, and then we can use this lemma just to prove what. So just what is our ideology to work with this equation? Okay, you see in this special variable which I have chosen, and just then, and for the perturbative problem, the choice of special variable, it is very well-known problem. So for example, in this famous problem of the stability of solar system, which was quite long ago invented KMC. It's only recently, it's only 2 or 3 years ago, the problem was done completely on the level of KMC. And this was done because finally people observed that when we consider Hamiltonian of solar system, we can choose a new set of independent variables, such that in these new independent variables, Hamiltonian of solar system looks especially nice. Something like this, but on much lower level, happens here. I introduced new complex coordinates, and in these new complex coordinates, Hamiltonian of beam equation looks like this, which is good for me. You see, it's a quadratical path, which is nice diagonal quadratic path, plus a nonlinear path of order 4. I wish to start the beam equation near the n-dimensional torus. And now, I have a radius vector for this torus, which is the action of the mode number s of the unperturbed motion. And of course, I want to perturb small solution because, as I said, no chance to understand how big solution looks like. So my plan is to perturb solution of size of order epsilon for the linear equation. That is to say that the vector rho will be something of size epsilon, and I will always consider the case when the vector rho belongs to n-dimensional cube of size epsilon, right? And so this will be another parameter which I will play with. So you remember I said that we have only hope to perturb only typical solution. Right? Typical, which means that the vector rho should be typical. Right, and now there is now I have to make really elementary change of coordinates. You see, I have this low coordinates which corresponds to the basic modes A for me, and I have high modes. Then I keep high modes unchanged, and for the low modes I will pass to the corresponding action and angle variables. Again, everybody with experience with Hamiltonian systems knows this transition, knows this change. It's an elementary change of variable. So you see what I do now. What I do now, I pass from a complex variable xi to the new variable angle theta, and to the action I, which is square root, which is just r squared, right? But it should be not r squared, it should be just shifted r squared. So this new set of variable, new set of actionable variable for the low modes, it is here. It is here, so these are just transformed coordinates, and the new variables, the unperturbed torques in the variant for the linear equation, it is like this. For the unperturbed motion, action equals to 0, and the angle varies through one-dimensional torques. And all other variables for the unperturbed motion are 0. So this is elementary preliminary transformation, and in the new variables, the Hamiltonian of the unperturbed motion looks in just extremely simple way. It used to be quadratical form. Now it is quadratical form on the variable L, which is apart from this finite set A, and from the variable of the set A, it is just a linear function. So now quadratical Hamiltonian looks like this. But now something new happens which we did not meet before in the KM theory. So now new finite set appears here. So this is a set of unperturbed modes. Unperturbed modes, and this is the rest. Now I have to consider new set, which is L finite, so the rest is L. Now I will, in this L, which is infinite set, I will find finite subset L subindex F, which is formed by poled point in lattice, which have the same length as some vector in this set. You see, so in this case, this point has the same length as this vector. These points have the same length of this vector, and I think I also have these points. You see, so I have to consider bigger points. So apart from the finite set of the original excited modes, I have to consider all points which have the same norms as one of the excited set. You see, this is the same picture as here. So this is the original excited set, and this is additional set. And this is the unperturbed Hamiltonian. So just a quadratical part looks like this. A quadratical part in high modes, linear function in the slow modes, and just plus higher order term. And assume that the set A is admissible for definition, right? Then and now finally comes the result. Then in the segment 1, 2, where, and I assume that the mass parameter is really parameter of my problem, and it belongs to the segment 1, 2, right? Then in this segment 1, 2, there is a set of zero measure, which corresponds to the very bad mass parameter of zero measure, right? Such that for any m outside of this zero measure set, we have a very nice normal form. That is that we can make one more change of variable such that after this one more change of variable, the Hamiltonian of the nonlinear beam equation looks in the following nice way. So now look what happens. So this is a quadratical part of the Hamiltonian. So in the low modes, which corresponds to the variable from A, it is the same. In the modes outside of the finite set A, it is the same. But for the modes for this new finite set, we have some new quadratic operator. This new quadratic form corresponds to a new symmetric complex matrix K of rho, which is of the same dimension as the set of these points, right? It's a new object which did not exist before. And now look what happens. So this matrix K of rho is a complex symmetric matrix which is small. Epsilon is the size of the solution which I perturb. This frequency which I have here, these are close to the unperturbed frequencies, right? And I have the rest. The rest is non-quadratic part of my Hamiltonian. And what is remarkable here is that the rest has the following form. The rest is a non-degenerate integrable part. 1 minutes. It's one slide apart from this. I'm really excited. So the rest is an integrable Hamiltonian. Integrable Hamiltonian means that it's a function which depends only on the actions, and these are my actions, plus a perturbation which is not integrable, but which is higher order part. And one more remark about this, about which is crucial about this new quadratical object which is here. That if I consider this symmetric operator, if I consider the corresponding Hamiltonian operator, this is the one which we have in Hamiltonian equation, right? That this Hamiltonian operator, for some choices of the set A is stable, and for some choices it is unstable. You see, so here something unusual for the KM theory happens. So we started with linear equation when solutions which you consider are stable. But now we arrived at a normal form where the corresponding solutions they may be unstable for some choices of this modes. And now the final result, the final KM theory. You see, so for each typical set, for each typical value of the mass parameter M, which I throw away because I cannot find this problem which Procesi and Procesi were fighting with for years. That's for any M outside of this measure set, I have a nice final result. You see, so there is a small, okay, let me remind you that this solution depends on the vector of this is the vector of the amplitude of the amplitude solution. Let us consider this as a new parameter. Then in this parameter belongs to the cube of size epsilon. Then in this cube of size epsilon, there is a small bad subset of the measure like epsilon to the positive degree, such that if this vector of the amplitude does not belong to the bad set, then the amplitude, then the real beam equation has a time for the periodic solution, has a time for the periodic solution, which is in some usual for the KM theory sense is close to the solution of a linear equation, right? And then this new solution, it may be linearly stable, may be linearly unstable. It is stable if and only if this matrix is stable. And so the final result that if d equal 1, if dimension is 1, right, then the constructed for the periodic solution always is stable. But if dimension d is bigger than 2, then for some admissible sets, the constructed solution of the nonlinear beam equation, they're just unstable. Why put it unread? Because this is very unusual for the KM theory. Then when starting from stable object, we constructed a new solution which is really unstable, and this is not because of tricks and because life is like this. I'm pretty sure that the same result holds for nonlinear wave equation, but also it's also a technical issue because this is theorem 1 is proved in a paper of something like 55 pages, theorem 2 it's another paper of something like 70 pages. And I'm very much afraid that just that I believe that we can do this job for the Klein-Gordon equation, but the size can just easily double. And then we have this usual question: should we pay this price to get new result or not? Pavel, should we? Okay. Thank you for your attention.
Any questions or comments?
Questions about unperturbed Hamiltonian. It contains Xi, K, eta K. Yes?
Yes.
It looks like the torus is hyperbolic one or not?
No. Because well, it is complex coordinates. It is elliptic.
Really, it is elliptic.
It is absolutely elliptic. So it becomes partially hyperbolic also because new matrix, which
Yes. Okay, it is elliptic. Where is the counter set?
Counter set sits in the set of admissible actions. Because I have a vector. I have a vector of the amplitude of the amplitude motion. This is the cube. Right? This is if n equal 2. Then vector of amplitude belongs to this cube, and there is this.
Here it is counter set.
Small measurement outside of this. You see, parameter n.
Thank you.
I have two different parameters now. The mass parameter and the vector of amplitude. They play very different roles.
Thank you.
Any other questions? If not, let's thank our speaker again. So we have maybe 3 minutes break.
So please use this.
It's already there.
This button. This button is one slide.
Where is the?
Yes, this is the point, and this is your yes. Forward. Okay.
You are very busy.
Is it sufficient?
The visitors are much more relaxed and the look is organized.
That'll be my question. So that's, you said it's necessary, but is it sufficient?
You can start.
So let us start a second talk, and it's my pleasure to introduce Professor Itai Shapley. And he will talk about asymptotic behavior of critical points of an energy involving circular wave potential.
Thank you. First, I would like to thank the organizing committee for giving me the opportunity to participate in the conference and to give a talk. Really like the organization here, and the young people are helping all the time. It's really very nice. This is a joint work with Petru Mironescu from the University Lyon 1.
Can you speak up or
This is a joint work. Can you hear me now?
Yeah.
I want to find the equilibrium to be heard, but to let people that want to sleep, not to disturb them. This will be too worst, I think. Yeah, this will disturb sleeping people. Yeah. So let's see. First, I would like to give to do some historical relevant results. So let's start with the Ginzburg-Landau minimizers. So we have G is a smooth bounded simply connected domain in R2. And we consider this Ginzburg-Landau type energy. Now, note that this energy was mentioned already before in the conference, but in the scalar case, where you took only scalar valued. Here, you take values in R2, or sometimes it's useful to look at it as complex valued. And we have a boundary condition. On G, we have a boundary condition, this little g, G going to S1, and it has degree D, which is positive, that it's greater or equal to 1. This is the interesting case. Negative case is the same. Zero case is less interesting. And the following result established about 20 years ago by Betuel-Brezis Delan, and they were able to describe the limiting behavior of the minimizers as epsilon goes to 0. So at the limit, there is a subsequence, so each subsequence, you can find a subsequence such that it will converge to this limit. So the limit is what can call a singular harmonic map with values in S1, and this is quite simple. So you have this factor, and here you see the singularities at the point A1 to AJ, to AD. The number is exactly D, the degree. And you have here a correction, this eta of z, ei eta of z, where eta of z is just an harmonic function, smooth harmonic function, and it's chosen such that this U star will satisfy the boundary condition G on the boundary. So for people who never saw such a problem, let me just very briefly describe what's going on here. So when epsilon is small, this term is a penalization term. So it penalizes if U or U epsilon is modulus is far from 1. So roughly speaking, U epsilon tries to be close to S1 as it can, but there is a problem. It cannot. It must. Every U epsilon must have a 0 somewhere because of Brouwer degree theory, because the boundary condition has degree D, which is different than 0. So there are also zeros, but most of the time it seems, or most of the area, you should be close to 1. And what Betuel-Brezis and Elan established is that they were able to describe what is going on with U epsilon, that there indeed the regions where U epsilon is not close to 1 in modulus are quite small, and in the limits they concentrate just near a finite number of points, exactly D points, and these are the points A1 to AD, which are the singularities of the limit. What the minimizer left from their zeros actually, when you pass to the limit. And what is also important to know is that the energy behaves like log epsilon. You have the exact coefficient in front, depending on the degree, and the O of 1 term is also very well prescribed, but I don't have time to discuss this here. Let me just mention, because the name Pozaev was mentioned here many times in the conference, that here too, Pozaev identity plays a major role, actually. Here, actually, the original result was only for star-shaped domains, exactly because there was the case you can apply Pozaev, and what Pozaev identity gives you, here it's not used to prove non-existence, but rather it plays a positive role. It gives you that the second term, the integral of this term, is bounded. Later, it was shown that for minimizers, the necessity of the star shapeness is not, it's not necessary. One can overcome it, and this was done by Struve in one method and by Del Pino and Fellmer with another nice observation. But in any case, positive identity plays a major role in all proofs. And also in the sequel, as we shall see. Now, let's move to the critical points. If your epsilon is a minimizer to energy from the previous slide, it satisfies this Euler-Lagrange equation. Yes? So one may consider then non-minimizing solutions. That is, solution of this equation, but which are not necessarily minimizers. Let me just recall a remark that was already made by Betel-Bozis and Elau, that if you consider general domains which are not simply connected, like annular domains, you may find solutions whose energy larger than log epsilon, actually of the order 1 over epsilon. You can take a boundary condition which is 1 on the inner boundary and -1 on the outer one, and then you get a kind of Motola Modica problem, and it's easy to analyze and to understand that you would get a minimizer in the scalar, for scalar value functions only, which is close to 1 here and close to -1 here outside. And in any case, the energy will be of the order 1 over epsilon, much larger than log epsilon. So one should take it into account. And what Betel-Bozis and Elau proved in the same book, actually, in one chapter, is that if we assume that G is star-shaped, this is necessary for Pozai, then a subsequence of the solutions, not necessarily minimized, converge, very similar to the previous case. You have singularities, but these times the degrees are not necessarily 1 or -1 even. So what you only know is that, of course, that the sum of the degrees should equal D, the degree of the boundary condition. And again, eta is an harmonic function, and you need this factor in order to satisfy the boundary condition. And the energy this time, of course, the behavior is still log epsilon, but the coefficient changes according to the degrees of the limit. So one may ask, do they exist non-minimizing solutions? So they do. First, if you consider the disk, the unit disk, and you take this boundary condition with degree greater or equal to 2, then it is easy to see that there exists solution of the Euler equation satisfying this ansatz. These radially symmetric solutions with factor EID theta. But these solutions for epsilon small are not minimizing. Why? Because of the first theorems that I showed you of Betel-Bozis and Elau, if the degree, say, is 2, for a large epsilon, for small epsilon, you will have 2 separate vortices. So it's far from being a function of this type. A more complicated construction is due to Frank Gualin. So he was able to construct mixed vortex anti-vortex solution, as he calls it. So there exists boundary conditions of degree 0 even, and solutions, corresponding solutions, such that in the limit you will have actually n pairs of vortices with singularities of degree +1 and -1. Okay? So +1 and -1 together cannot be minimizing according to the first theorem. So these are certainly different. And you can have a similar construction with degree different than 0. You can have still a product of things like this with degree 1 with points bj. So let's move to other problem. I consider what I want to do is to replace the potential of the Ginzburg-Landau by more general potential. I call it W. I call it a circular well potential. So the zero set of this W is a simple closed smooth curve in R2, which is denoted by gamma. It's not necessarily the circle. It's everywhere non-negative, but the zero set is exactly this curve gamma. I talked about this problem several times, and then also in Israel, and people in Israel are most, they're less polite sometimes, and then somebody made the remark that maybe this term is not very good because it gives the impression that you are talking about gamma, which is a circle, and I want to allow a more general curve, but okay, it is anyhow between quotes. What we assume some generic assumption about W, the behavior near gamma is like the distance to the power 2. It is smooth also, of course, and there is some coercivity conditions for large value of modulo X that is needed later, about the behavior at infinity. And without loss of generality, you can assume that the length of the curve gamma is 2 pi, the same as the unit circle. And let's consider again a bounded smooth star-shaped domain and a boundary condition, but this time the boundary condition takes its value into gamma, the zero set of W, and consider critical points for this energy. So you see I replace the 1 minus modulus U square by this W. And the Euler-Lagrange equation is this one. Okay, this is actually the issue, and we have a theorem that the subsequence converge to a limit, so it's really what you expect. It's a singular, one can say, gamma valued harmonic map, taking value in gamma. And in order to describe it, it's really the image of some map from the previous theorem of the Ginsburg-Lambda case, but you can use the map tau, which is an arc length parameterization of gamma defined on S1. So the result is not really surprising. Our interest, at least in this problem, is that in order to prove it, we couldn't use the method by Bethuel-Brazis alone. At some point, some other argument was needed, and I will try to explain later where exactly the difficulty arises. Let me just remark that for minimizers, we have a similar result, but there the degrees are necessarily of degree 1 if G is of the positive degree D. And for minimizers, the problem is easier because you can really use the known methods. Because for minimizer, in order to get energy estimates, to get some upper bound, you can just use your own test functions that you construct by hand. The problem with arbitrary solutions is that you have to find to start from scratch. You don't have a priori any bound on the energy, and the problem is more difficult. So here's a picture. This is the domain. You have G is prescribed on the boundary of omega. Actually, it should be G. Yeah, it should be G. And in the limit, you will find the finite number of singularities, and the epsilon, essentially, it goes here. And most of the time, the values will be close to gamma. Of most of the domain, the values will be close to gamma, and except some errors around these points where all the interior of gamma is covered. Okay, so this is towards the end of the conference. People are already tired, so just one result, and I will give just a sketch of this result, and that's all. Okay, after all I said that we can work for a general gamma, now I switch for simplicity of presentation to the case where gamma is S1. So it looks like Ginsburg-Lambda, but not really, because we don't assume that W is a function of the modulus only. If it is a function of the modulus only, like in Ginsburg-Lambda, it would be the same. But we don't assume this, and it helps me. It doesn't change much. The difficulty is the same, but in terms of notation, it's really saved me a lot, otherwise we have to, most of you already done it. You have to introduce coordinates near the boundary of gamma, distance to gamma, sign distance to gamma, and some parameter running on the curve, while for the circle, we have the polar coordinates, which are very known and very convenient. So actually, in this case, we can write the potential W really as a form very similar to the Ginzburg lambda. So we can really divide by 1 minus modulus V squared. But the coefficient here is not necessarily 1. And moreover, we do not assume, even if it's a function, we not necessarily assume, we can, of course, but we don't assume that it's a function of the modulus only. Because then it would be like the previous case, actually. As I mentioned here, alpha is 1 in the Ginzburg lambda case. So locally in omega, probably it's G, you can write V epsilon as rho epsilon ei phi epsilon. That is, use just polar coordinates. Rho epsilon is the modulus, and phi epsilon is the modulus. Why I say locally? Because the phase is not globally defined, because of this problem of degrees. Phi is just defined locally, rho epsilon is defined everywhere. So phi epsilon is actually defined as set-valued function, but you have you can add multiples, integer multiples of 2 pi. So if we use this coordinate and we write W like this as a function of rho and phi, so rho and phi are polar coordinates in the image. And alpha should be 2 pi periodic, because phi, because of the values of phi. And if we write, at least locally, what is the Euler-Lagrange equation? Remember, the Euler-Lagrange equation in terms of V epsilon is very simple. It's Laplacian V epsilon equal gradient of W at V epsilon divided by epsilon square. If you write it in terms of the new coordinate rho and phi, you get a system of equations, one for rho, this is one, the second one is for rho, and the first one is for the phase phi. And note that for the Ginzburg lambda case, you get 0 here. The equation for phi is really very, very nice. It's just a simple elliptic equation, homogeneous elliptic equation, while here you have this nasty term because alpha phi, well, it's a coefficient. It's not necessarily 0. And then you have something involving epsilon square in the denominator, and this is not very nice. So this is really the main difficulty we have here with respect to Ginzburg lambda. Now, when you start the analysis, actually you can do quite a few basic steps which work just as in the Ginzburg lambda case. And it's also in the proof of Bethuel-Brazil-Celan. The first steps are easy, and then you get to a point where the difficulty arises. So let me go over the steps. First posyde is identity essential here. This gives you two things actually. Not only is that the second term, the potential term of the energy is bounded, but also that the integral of the normal derivative square on the boundary is also bounded. This is also useful. But this is, of course, because we use that the domain is star-shaped. Otherwise, we don't know what to do. Now, these coercivity conditions that I assume at W, it ensures that V epsilon at least remain bounded. So there is some bound for V epsilon. And then, using standard elliptic estimates, you get that the gradient of the solution is bounded by C over epsilon, which is also very useful. And then there is a nice construction by Bethuel-Brazil-Celan of the bed disks. So you can, you look at the bed set. The bed set is where the modulus is less than 1/2 say. In particular, it includes the zeros. So you can cover them by a finite number of disks of radius of order epsilon, lambda epsilon. When I say finite, I mean that the number is uniformly bounded in epsilon. So passing to a subsequence, you can even assume that this is constant all the way for every epsilon. Now, we know that the phase is what gives us problem. For rho, we don't have actually problems from the start. It's actually a small new observations that we made that wasn't noticed before, that quite easily from the start you can get L2, the L2 norm of the gradient of rho is bounded by Gallardo-Nirenberg inequality. And then what you, outside this bed disk, which include the zeros, you can write V epsilon as the modulus times a factor. This really gives you the information about the degrees. The theta j are just polar coordinates around the point xj, the centers of the bed disk. And eta is a smooth function, globally defined. And let me mention also that because of this bound on the gradient, the degrees are also bounded. So bounded uniformly in epsilon, and after passing to a subsequence can be assumed to be known and constant. So it looks like, let me just show you the picture, that it's almost done here. We already see the end of the story somehow. So these are the bed disks. What may happen is that you may have several disks coming together, not like in this picture. And when epsilon goes to 0, these bed disks stick together to a common point, which is some point A1, say. And the others will go to A2, A3. And this A1, A2, A3, etc. are what we expect to be the singular points of the limit U star, the S1 valued singular map. But so it looks like we see the end of the story, but our problem is with eta. Eta may do nasty variations. It's a smooth function, but it may do a lot of variations, and we don't have a priori any estimates of its energy. We want to control it. This is actually the main issue. Bertrand-Brézé-Célin use one method that we cannot apply here. And actually, we are going to see a simpler argument in order to achieve it. First, I want to show you an auxiliary result in a simply connected domain, a maximum principle that will be very useful in the sequence. So we consider a solution of the Euler-Lagrange equation. Write it as rho ei phi. This is rho epsilon, and this is phi epsilon. We assume that it is close enough to 1 in modulus, that the values are close enough to the unit circle. And it is in a simply connected domain. So phi here is globally defined, no problem. I remind you the equations. We want a maximum principle to phi, and phi is, well, we have a problem here, because on the right-hand side we have something divided by epsilon squared. We know that the right-hand side is in L1, okay, but it doesn't have a particular sign. And a priori, we don't see why a maximum principle would be valid here. But we have propositions that indeed we have a maximum principle holds here. And in order to achieve it, we don't apply it directly to phi, but actually to phi minus some constant times 1 minus rho squared over 2, or plus for the maximum. And for these two functions, we have a minimum and maximum principle. What is the trick here? The second equation is actually very nice. And when you do some manipulation and you look what is the equation satisfied by 1 minus rho squared using this, and you see that actually you can overcome these nasty terms with terms that coming from the equation for this function. It's one has to play around with some parameter, etc., but finally one can achieve it. And the fact that we had is that it's not applied to phi itself, but you have to subtract some function. It's not really a problem for us in what we should, in the way we are going to use it, because we are going to bound phi by large quantities, and all the O(1) terms, like this one, doesn't make any change. So this is not a problem. But in looking for the future, already, the bad disk that we defined before by asking the rho to be less than 1/2, now we are more careful and we ask them to be less than rho 1 minus delta 1, where delta 1 is given by this, this proposition. And of course, this is not a problem. The new balls, the new bad disk will be larger than the previous one. The number will be still finite, and there is no problem with that. And the remarks that I made before, that in the Ginsburg-Lambda case, the expression for phi is just this equation, and you have directly the minimum and the maximum principle, and you don't have to work at all. And now another remark, why we cannot use the method of BBH, better process alone. Their proof is based on some splitting of the gradient of the function, U epsilon or V epsilon, and it based on this identity. This is a very nice identity that you have this field here with divergence 0. Now, why this formula is valid in the Ginsburg-Lambda case is very easy. You just do the computation. So when you derive, say, this vector product, the first possibility is to derive this guy, but this guy will give you 0 multiplied by itself. So you only get contribution from V epsilon times the second derivative with respect to x1. You add it together, you get V epsilon times the Laplacian. But the Laplacian, because of the Euler-Lagrange equation and the particular form of the potential, Ginsburg-Lambda potential, it's a multiple of V epsilon. So again, you have V epsilon times some factor times V epsilon, the vector product is 0. In our case, with the general W, we don't have it. We looked, we feel that somewhere is hiding some analogous result to analogous formula to this, but we weren't able to do it. Okay. The first step, good news for you, it's also the last step, yes? So I just want to show you how we start. Because, as I said, we have solutions of the equation, and we have to start from scratch to get some good estimate of the energy. Now, the log epsilon order energy is really what we look for. Because this is, we know that this is a sign of the vortices. And once you get this first step, you can continue. Also, there's some ideas needed, but this is the starting point. I will just give you later at the end an idea of the next steps. But mainly I want to concentrate on this step and to show you how this maximum principle in particular is relevant here. So we denote by G epsilon the perforated domain when we took out from G the bed disk. And now, again, we know that the problem we have with V epsilon is its phase. Its phase, V epsilon, is not globally defined. So, of course, the easy way to get around is to somehow take the factor of the degrees. This is, you can write it also as EI theta J dj. And when you took out you divided by the degrees, you are left with some S1 valued map without degrees, so you can write, you can do a lifting and find the map eta. And our problem, again, I wrote it already before, our problem is actually with eta, how to control eta. And this is where we have a trick. There were bad disks, now we have good rays. For each of the bed disks, we look at the center, and then we look at the ray starting from the center in some angle between 0 and 2 pi. Actually, it's not a ray, it's a segment. It's segment because you intersect the boundary of G at the end sometimes. So you can find a ray that it has direction such that the variation, the L1 variation along the ray of eta is bounded by this term. This is actually trivial because you know that in average, well, it will be 1 over 2 pi, the overall energy of eta when you go over the rays, because you have 2 pi possibilities for the angle. So you can find some ray, some direction in which it will be less than 2 times the average, say. Instead of 2 pi, I divided by pi, so it's 2 times bigger. And then you do the computation and use Cauchy-Schwarz. So you divide by r and multiply again. This is the way it appears in the energy on the whole domain, yes? And that's why you have this bound for this guy. And here you see where the log epsilon comes from, or one way to see where log epsilon comes from, it's from this second integral of 1 over r, starting from a multiple of epsilon up to somewhere bounded value delta j when you hit the boundary of your domain. Let's look at the picture. So what you do, say at each of the points, say you have 3 points, for x1 you put r1, x2, r2, a good r2, a good rc. Now what you are left with, the domain without the perforated domain, but also without these segments, now it's a simply connected domain that we denote by eta epsilon. Yes? G epsilon, the perforated domain, minus the rays. And now, in eta epsilon, the phase of phi epsilon, the phase of v epsilon is now globally defined because it's a simply connected domain. We don't have any problem here. And you can now define the version of it using eta. And theta j now, instead of taking the usual theta j with values between 0 and 2 pi, since you took out here a segment with angle alpha 1, you take it in the corresponding interval, of course. And now, we know we have the bound that we got from the previous lemma, that was this, for the integral of gradient omega over a ray. Actually, it gives you an L infinity bound on the boundary of this perforated domain, because on the outer boundary, eta is bounded because of the boundary condition, which is G, which induces some, the value of eta is fixed there. And here, the variation of eta is bounded by this term. So all the way here, all the way on the boundary, either on the ray or on the outer boundary, you know it in advance. Also, on the small circles, you know also that eta is actually bounded by this bound, because here the variation of eta is small, is not so big. Actually, it's O of 1, because the gradient is of the order 1 over epsilon for one of the estimates that I gave you, and the perimeter of this disk is also of the order epsilon. So eta just changes O of 1. Can change in a quantity of O of 1 along the circle. So you have this bound. And if you have it for eta, you have it for phi, because phi, the difference between phi and eta is just some multiples of 2 pi with dj. So it's O of 1. Okay. Now we apply the maximum principle. So in this simply connected domain, we can apply the previous maximum principle for phi and get that the L infinity of phi in the whole domain eta epsilon is bounded by the same thing. Of course, it's not sorry because it's eta is a function itself, but we will use it later. And then you can go back to eta. The difference between eta and phi everywhere is just O of 1. So now it's the L infinity norm of eta. Now you can forget about your race. Eta is defined everywhere in this perforated domain. It's still bounded by this bound. But still you have eta on the left-hand side, eta on the right-hand side. But what you do now, you use the equation. In the equation, I show you the equation for phi. The equation for eta is very similar. You just have another term on the right-hand side. In particular, you have what you added on the right-hand side for phi. In the equation I showed you before, it was this term with 1 minus rho square over epsilon square times alpha phi, I think. This we know is O of 1. It's O of 1. So when you test with eta and do integration by parts, you get on the left-hand side you get the L2 norm of the gradient of eta. On the right-hand side, you get a term that is multiplied by eta. Yes, we test with eta, and you use this term, and say for the term that multiply this, which is bounded in L1, you just get this on the right-hand side. So you see, you have gradient, the norm, the L2 norm of gradient eta squared bounded by this term. This, of course, implies this bound. Yeah? So you are finished, and then you can go back to phi. So phi is not globally defined, but its gradient is globally defined. And for phi, you have the same estimate, actually. Why? Because in phi, you have eta plus some sum of dj theta j. Now, the gradient of theta j is 1 over rj. So the energy of 1 over rj is also of the order log epsilon, because we are doing the computation outside r, or rj bigger than epsilon. So you also get log epsilon for the other term. So we got this. And this is actually the end of the first step, because it gives you the log epsilon estimate for the energy. So now, as I promised, just I released what are the next steps. So first, the first step. This is actually what I showed you, the idea. A log epsilon order of the energy. The second step uses the first step as well as elliptic estimates of the type of Stampakia. And what you get is that you get actually finally something which is really bounded, not something just log epsilon, something which is really bounded, but the norm in LP for B strictly less than 2 is bounded. This is really a good step, because here you can even now pass to the limit for you have a big convergence of the sequence in W1P. But this is not exactly the way we are going. What we do next, we first recognize what will be the singularities of the limiting map. This is actually what we saw already before. It's the limit of the centers of the bed disk. Some may go, a couple may go, a pair may go to the same limit, of course. So K, the number of bed disks, may be strictly larger than the size of the singularities of the limit. And then we show actually that the energy is bounded outside a disk around this limiting point. Okay. So this is now the size this time is bounded. So now we are in a fixed domain outside the singularities, and here we have already finite energy. When you have finite energy, you are now in business. You can apply your machine and do some work, or it's some work, but not necessarily too difficult. And you can, using this bound, you can get convergence on each compact domain of the domain without the singular point. There are other issues, of course, about the location of the points and about the further characterization of the limiting map, but this is more. I don't think it's necessary to discuss it here. So this is already what I wanted to show, that you have actually this convergence that I stated in the material, which is uniformly converges outside, on each compact set outside the singular points. And since I don't have a corresponding slide, please thank you for your attention. I say it loudly. Thank you very much.
So, any questions or comment?
One would like to have similar situation. Now you have a phase prescribed, but if you look at magnetics, you would like to map in S2. Have you looked at that too? Similar type of questions?
You mean in higher dimension?
Yes, higher dimension in the image, because if you look at magnetic fields, where we would like to characterize all other, you have now constructed in this way singular solutions, which are important for the magnetics, but then you usually have a map in S2 because it's a direction in space.
Your domain is in...
Domain you could think of 2D or 3D, probably more realistic would be 3D. And then I know a little bit this question, maybe it has been treated, but the problem of describing the singularities, getting a good approach, there has been computations on that.
There are problems, I don't know exactly what you mean, but problems in liquid crystals.
Yes, this is one.
That you have the maps in S2, but if you want to relax it, you mean also with epsilon instead of...
You can do this relaxation. Yes, you can do that. It's more complicated, but you can do that.
Yeah, there the energy is bounded.
Yes.
No,
but
maybe it was done, I'm not sure.
No, I mean, the case you consider in the harmonic maps is a special case because the singular solutions are not in the Sobolev spaces, whereas in higher dimensions they are in Sobolev spaces, but for applications in magnetics, which is also closely related to Ginzburg-Landau, we have to get the S2, and as far I'm now sometime out of this business, but I'm not sure how far this similar problem has been solved analytically. Numerically, they try to do that.
I'm not aware of it.
Okay. Maybe we can discuss.
Yeah, sure.
Any other question?
I would like to know if you make more complicated the zero set of the potential well. For example, if you have two concentric curves, what could happen?
Yeah, well, actually, there is a work of mine with actually your ex-colleague Nelly André about this problem. Yeah. But there we looked at the problem more, it's more a problem related to the Modica problem, but when the potential. So Steinberg, for example, introduced this problem. We have also a kind of a constraint, not boundary condition, but rather with some constraint on our of the integral of modulus U. And then we actually somehow the results are more interesting because then finally you get what you expect. There you find some interesting phenomena.
Yeah, concerning the position of the AIs, are they influenced by the alpha V? I mean the No.
Actually, all the problems that we had and I struggled here and also during the conference. Somehow, when you pass to the limit and try to calculate it, disappear all the. It's really the same thing. So it's a question about harmonic maps with values in a curve or in S1, in curve in S1 it's the same actually. So you don't you don't find anything new from the potential here. The potential finishes its job in the convergence, and while you have the limit, it's not related anymore to the potential, but to curve, to S1 curve, but curve is not more complicated than S1, it's the same. That's why I'm a little bit saying you don't find many interesting things because of the potential here, just difficulties in the view.
Okay, so let's thank speaker again. Thank you.
Dear colleagues, one moment. Thank you. One announcement from organizing committee. Российские участники, повышение квалификации свидетельства готово. Подойдите, пожалуйста, в оргкомитет, там нужно будет расписаться и получить. Хорошо, те, кто вставали документы. Спасибо. Sorry, it was only for Russian participants.
He will talk about optimal experimental design for the nonlinear dynamical models. Please.
No. Good morning, friends and colleagues. Thank you very much, Mr. Chairman, for the introduction. And I first want to thank the Professor Skubachevsky and the organizers to give me the chance to talk about our research in Heidelberg on this excellent conference, and to be in Moscow this time of the year. What I'll be talking about today is it's maybe not quite exactly in the mainstream of the main topic of the conference, because it's on optimization, but connected with differential equations. And just a second. So what I'm really talking about here is model validation. So the question, of course, is you have differential equations models, and you would like to validate them with by the hand of experimental data. And what I'm talking about is joint work with the Heidelberg Optimization Group, with Professor Kostina, with colleagues from BASF and Degussa, two German companies, and also with a team of Samuel Bandara and Thomas Meyer of Stanford University. So first I want to start with two quotations. So you know this one, which is over 30 years old, claiming that high technology is essentially a mathematical technology. And 20 years ago, we had a similar quote from another chemist, the Vice President for Research of BASF, Hans-Jochen Quadbeck-Seeger, saying that in terms of mathematical optimization, that it has developed into an attractive instrument for industrial practice, offers new opportunities for optimizing particularly complex processes, and completely new insights are gained. This allows us to advance from trial and error to a strategical approach. So how comes that mathematics has such a major impact on industrial practice? And I want to try to explain first what he means by from trial and error to a strategical approach. Now, classically, the industrial approach is to use trial and error empirically on the real process, so the real experiment. However, meanwhile, we have detailed mathematical models, and we have also efficient simulation and optimization methods. And so research and development, not only in science and engineering at the universities and in academia, but also in industry, has significantly transformed. And there's this new approach, strategical approach, that our industrial colleagues also call rational design, to use parameterized model world, the modeling and the simulation that we have, in order to come up with optimal solutions to their problems. And they see that there is a huge potential for innovative solutions. However, in order to be able to exploit this potential, what we really need is not only detailed mathematical models, but they have to be calibrated to be quantitatively correct. And that calls, with the complexity of the models that we are using, calls for new mathematical research and mathematical methods. So this is a brief overview. So the problem I'm talking about is optimum experimental design for the validation of models for nonlinear dynamic processes. And the approach is to use optimization-based methods. So first I will briefly introduce parameter estimation, then talk about some elementary covariance analysis and confidence regions. And then I will go to the topic of the talk, design of optimal experiments and how to solve these kind of non-standard optimal control problems. And I will end with some real-time methods for optimum experimental design. So I will also give you 4 case studies that are all from some elementary ones, but difficult enough, and they're all from industrial practice. So let me describe this cycle of model validation. So originally, we will start, say, with some experiments, and we have some data, and then we start the modeling from the observed process, we will get some equations and possibly some good simulation solutions to our model. And then we would like to use this for optimizing a process or for control purposes. However, then we have to calibrate them, and that's the problem of parameter estimation, so to determine the correct parameters of our model. However, unfortunately, in most cases, it doesn't look as nice as it does here, and then we have to revise both the model and also the experiment, so we have to come up with new experimental data to be sure. And here is this is the stage where the optimum experimental design can help us, both for getting better experiments, but also for discriminating between possible modeling alternatives. So let me first start quickly with parameter estimation, although everybody in the audience probably knows. So what we have, the models I'm talking about are differential algebraic equations, where the P here are the unknown system parameters that we would like to determine in order to calibrate our model. But there is also the Q, which are control parameters, and the U, which are time-dependent control functions, which we can use to design optimal experiments because there are decision variables in the system. And Y and Z are differential and or algebraic states. And depending on the functions or operators F and G, we can have ODEs or DIEs or non-stationary PDEs, which will be the final example that I have. And they can be pretty complex. What we have to face in industry is that they are nonlinear. They typically also have state-dependent discontinuities. They can be stiff or usually are stiff, but they can also be unstable. And they have all kinds of different timescales, and that's a problem of numerics that has to be taken care of. Parameter estimation. So assume that we have some data, so some measurements of our process, of functions of our process B. Then we have to solve a constraint approximation problem to determine the parameters and the trajectory, the solution of our problem such that in some suitably weighted norm, we approximate the data optimally subject to the model equations and certain additional constraints that we may have. And the classical approach is generalized Gauss-Newton methods developed by Carl Friedrich Gauss a little over 200 years ago, and other people that have worked on the topic later on. Let me start with one example, satellite orbit determination. Now this is an interesting problem because you may have read the newspaper that last week the launch of 2 satellites of the German GPS system Galileo did not end up in the orbit that they were supposed to be. So the 2 satellites were lost, and indeed the launch ended up at, this is a different example, ended up at an apogee of 17,000 kilometers, but they should have been at 23,000 kilometers, and at 17,000 kilometers they are not useful. So what we lose there is 2 satellites, where the worth of the 2 satellites is already 80 million euros. Not to talk about the launch itself, the Soyuz that is now wasted, and all the time of the people, and that we have to wait for another year before this can be repaired. So this is another example that ESA wanted us to use as a benchmark for mathematical methods to be developed. That was the Ariane 5 launcher in 2002 and the Artemis satellite. And there the transfer orbit also was too low. It was not the 36,000 geostationary orbit that was supposed to be the target, but rather only at an ellipsoidal orbit of 17,000 kilometers apogee. So when that happens, such a faulty launch, then very fast, and you need fast and reliable mathematical methods in order to determine the actual orbit, and then hope that there is enough fuel on board so that you can correct and actually end up at at the orbit that was desired. So, as I already said, if you don't do that, you use really many millions of euros. So, in this particular problem, we have model equations which are actually just 6 ODEs, velocities and positions, but they're very detailed Kepler equations, including all external forces such like air drag, solar light pressure, the gravity of the moon, gravity of Mars and Venus, and everything that influences the differential equations up to the 9th decimal. So that's a very detailed dynamics, including also that the Earth is not symmetric. But the mathematical difficulty here is that this is a time-critical problem. You need the solution within the first half hour or 1 hour before the satellite enters the atmosphere again, if it was a faulty launch. That happens. So we have to react quickly, and we need reliable methods to determine that. And of course, that's not the computational complexity, but you really have to get the solution within like half an hour. And there are very few measurements that you get, and in our case, just from two ground stations, one in Perth and one in Malindi. And during the first hour, all we get is 8 measurements of the range, of the distance to the satellite, and 3 measurements of 2 angles, the polar angles. And few more if we wait for another orbit. And this is a very ill-conditioned problem with outliers. So these are the measurements that you can get within 2 hours. And we had to develop new algorithms, so new globalization strategies were necessary, new initialization strategies. You may wonder, I mean, ESA has a lot of money, and of course they did have some software before and spent a lot of it, except it didn't work and it wasn't reliable. And that happens even in this 21st century. So they needed new methods here, particularly because of the outliers and the globalization of the convergence. And we were able to do that, and the new method that we developed in all kinds of cases always solved the problem, but the methods that they actually had worked only in about half of the test cases. So that was very unreliable, and in terms of 80 million euros at least at stake, that's really a problem. So, but we were able to solve the problem, and here you see the few measurements that you only have to actually solve the problem on the first orbit. And there is one problem if you plan the next launch. You assume that of course it might be wrong. So there may be an error in the orbit, in the initial orbit, and then to do an a priori analysis whether the estimation problem is actually well posed from the measurements you will get from the first half hour. And that's an experimental design or sampling design problem already. But I'll give you a few more. So that's one of the optimization problems that we have to solve. Now, some brief words. I'm not going into very much detail here about simultaneous methods for optimization with differential equations that we are using. So the idea is you discretize the controls, you discretize the states, in particular the boundary value problem or the differential equations, and then simultaneously you solve the optimization problem and the discretized boundary value problem, plus further constraints that you have, and you do that in one loop. And multiple shooting that I show on the next slide that we've developed for this case is one of the most versatile methods. And what are the advantages? You get much better local and global convergence than with other methods, and you have numerical stability that you can prove. It's parallelizable, so it has a number of advantages. So this is multiple shooting, so you solve your solution piecewise, and then of course this is discontinuous at the beginning, but at the end of your optimization process, of course, you have to solve the boundary value problem. So these jumps here, the discontinuities have to vanish. The non-consistency of algebraic equations also has to vanish so that you get these additional side conditions. Okay, now this discretized problem of parameter estimation then is a constraint, a large-scale constrained equality and inequality constraint least squares problem where the boundary value problem is in here. And you can solve such a constraint optimization problem with the generalized Gauss-Newton method. So essentially, you improve any iterate with the step size and a correction term delta xk, which solves a constraint least squares, linear least squares problem. And I'm just mentioning this because it's important that, that these linear problems here can be solved by a generalized inverse. A generalized inverse that satisfies it's an outer inverse, which is an important fact in the convergent proof that you have here. What you can show that you get linear convergence if, and with a good asymptotic rate kappa, but the kappa rate kappa depends on whether you have good data and whether it's a well-conditioned problem. And in principle, this method is also globally convergent. So let me start with an enzyme example from enzyme reaction kinetics. There was a problem that we solved together with Degussa. So enzymes are industrial biocatalysts. We were investigating Novozyme or Candida antarctica, a yeast. And then in order to do experiments, you have a very expensive evaluation because you want to observe the stability behavior, and that usually takes days. So these experiments are maybe not so costly in terms of material, but in terms of time. And it's really a simple nonlinear differential equation. So you have the native enzyme that unfolds to the unfolded enzyme, but this can also react back to the native enzyme, and both can react to the deactivated enzyme. I should also say that maybe these enzymes are important industrial biocatalysts. You will find them in any detergent, for instance, your washing powder, but also in other substances. So the mathematical problem is we have mass action kinetics. That's an ODE with only 4 state variables, but it's nonlinear because you have a temperature dependence in the Arrhenius kinetics. And there are 8 unknown reaction rate parameters that you need to estimate, but what we really want to know are the stability quantities, the so-called total turnover, and the half-life of the enzymes. And if we design an experiment, the only thing we can do that we can influence is the control function, which is the choice of the temperature profile. It's the only option to optimize anything. And we can not measure any of the substances, but only the amount of acid they produce during the reaction, because there is a control there that adds base to keep the pH value constant. That's the only thing you can measure. And we will see that this problem is very ill-conditioned, and from these data, a single experiment doesn't help you. You cannot estimate them. So here is an example. This is the classical temperature profile for a standard industrial experiment for enzymes. And these are the measurements that you get. And what you see here is the result of the optimization problem. So you get a very good fit to the experimental data. But you ask yourself, of course, well, looks good, but do we know the parameters now? And the problem, so is the parameter estimate reliable? And in order to be able to judge the accuracy of the parameter estimate, I have to do a little bit of elementary statistics. So the problem is when your measurements are noisy, they have a measurement error, then the estimate that you get is of course also noisy. It's also a random variable, and up to first order, you can describe this by this generalized inverse, J plus, and you just do this Taylor expansion, then you see what first order is the distribution of your parameter estimates, and from that you can conclude the covariance matrix. And in the case that you don't have constraints and the measurements are normally distributed with zero mean. That's the classical covariance analysis that everybody knows from school. So, go a little bit further. From this covariance matrix, or the generalized inverse, we can then derive a confidence region for the where the true parameter value should be. And this confidence region here can be also enclosed by a confidence box, which is just this 2 times delta I, and delta I is just the square root of the statistical quantile, where alpha is the error probability. So these are what people typically name the standard deviations. So now we have a measure for the quality of our parameters, and now we look at this fit again, which looks okay, and these are the results. So this fit here means 4 parameters, well, they look as if they are well determined, but 4 other parameters are totally undetermined, totally uncertain. And since the parameters depend on each other, if these 4 parameters are uncertain, then also these data here are totally misleading. So, the next question, of course, is why does the industry actually need calibrated models? In particular, the chemical industry that delivers these applications here. So one thing is, such a validated model allows what the industry calls virtual laboratory. So if you have, for such a process in a chemical plant, you have a well-validated model, you can upscale from the laboratorium to the production plant. And what you try to avoid is a pilot plant that is typically built in between. That's a very costly effect, and in particular it costs a lot of time. On the other hand, if you have a very accurate model, you can base the whole process design and the control and the optimization of the plant and of the process on this, and then you get better purities, better selectivity, higher safety, better productivity, and in particular you can also avoid waste, energy, raw products, you have lower cost for the raw products, so you can win with mathematical theory behind it. But if the experiments that you have are not sufficient to actually give you precise estimates of for your model and the parameters in your model, then of course you waste material, energy, personal cost, and a lot of time on these experiments. And even worse, there may be a disaster if you base your planning on the wrong parameter values. And the final example in my talk is one where we're talking about avoiding millions of loss of money. So question is, can we do better? And now this is the problem of design of experiments. Let me give another example here, the urethane reaction experiment of our partner BASF. So that's a chemical reaction here with these substances. You start with isocyanate and butanol, you put that into a vessel with solution in there, and then it starts reacting to urethane, to allophonate, and there's also the solvent in here, DMSO. And there's some intermediate product, isocyanurate. And then the question here arises, what to measure and when to measure. We are given 3 alternatives, which are costly, 3 analysis methods with which we can either measure substance A, or measure substance C and D, or measure substance E, and all at different accuracy and different cost. But they take a while. So the second question is then, what should be the times when we do these measurements? Because the process is reacting and you have different effect at different times. And what can we choose as experimental conditions? This time we have 3 control functions. We can choose the temperature and the 2 feed streams for the vessel. And we have 7 parameters that we can adjust, namely the initial concentrations of the substances in the vessel and also the volume of the reaction vessel. And we have to satisfy a number of constraints. So there are safety constraints in terms of temperature, there are cost limits. For BASF is very important. These experiments take longer than a day, and BASF closes at 5. So no measurements after 5 p.m. And during the night, not too high temperatures because there are no people there in order to take care of the reaction. And you also have to observe trade union restrictions on lunch breaks and so on, which are actually serious problems in an optimization problem. I'm not kidding. So in general, now we conclude we have to choose experimental conditions, which could be control functions, like temperature profiles of feed streams, certain parameters that we can adjust, and there's also the sampling design, namely when and what to measure, which is an integer problem. So that's an integer optimization problem, because of course we can only do entire numbers as numbers of measurements. So then the question arises about what is the cost function we want to minimize. In our case, we want to minimize the uncertainty of our parameters. In other words, we want to minimize, in order, or the prediction error of the process model, which is for us, we want to minimize the function of our covariance matrix, subject to constraints. One which is quite important is, for instance, you have to make sure that you stay with your experimental design in the domain of validity of your model, like it should be a Newtonian fluid and not non-Newtonian, and so on. So, the cost function we choose is we minimize the function of the covariance matrix, such as the trace or the maximum scaled trace, or the maximum of the standard deviations subject to our discretized model equations and the state and control constraints. This is not a standard optimal control or optimization problem, so it's not easy to solve it actually, because it's a nonlinear optimal control problem and it's a mixed integer optimal control problem. So some of the control variables can only take integer values, which is a serious problem because there is not much of a theory for this. Then, although I should say the Pontryagin maximum is valid also for integer valued controls. However, this is not a normal control problem also in the sense that the cost function is defined by the generalized inverse and the covariance matrix, and so it depends already on first order derivatives of our parameter estimation problem. So we need higher order derivatives in order to come to optimization, which is not so trivial for a complex problem. So the next question is, if we have to derive new methods to solve such problems, is it worth it? Will we gain just a few percents, or is typically in optimization, or can we have substantial improvements? And here is the surprise. This is a nice example. It's a toy example, but it's wonderful to see what happens. Was developed by students in the group of Professor Kostina. So this is a robot, and for offline programming of robots, you need precisely calibrated models and very expensive experiments. So for instance, the dynamic parameters like the mass distributions, the inertia, are only very approximately known. And even the kinematic parameters like the geometry, the angles, they have a high precision in itself, but they don't agree with what they should be, because the manufacturing is not so precise. So, here we have two examples. The left-hand case, we just want to identify two inertial parameters for such a so-called SCARA robot. And all we measure is the positions of the tool center point here. And on the left, you see like a standard experiment that we start with. And on the right, you see an optimized experiment. And they don't look all that different. I can see anything on the screen here. So, what do we see? Well, if you use just this experiment, you get the parameters with a certain accuracy. If you use this experiment, they are 10 times more accurate. In statistical asymptotics, pardon? Okay, that's the standard experiment. That's the optimal experiment. This means that this experiment is equivalent to 99 repetitions of this experiment. So what we gain by this experiment is 99% improvement. So, and that's quite typical in optimum experiment design. The gains in information and in accuracy are huge. So there has been a lot of work in order to come up with good methods for such problems. The original idea of optimum experimental design came up in the 50s. There's the early work of Kiefer and Wolfowitz, of Box and Draper later in the 80s, and Puckelsheim in Augsburg in 93. But none of this was all for linear problems, none of this was for nonlinear problems, and none of this was for differential equations. So, so there was a lot of work to do here actually since the last about 15 years. So new optimization methods had to be developed. Also a particular problem for complex models was the efficient evaluation of higher order derivatives needed for this problem. New methods also to solve nonlinear mixed integer optimal control problems, real-time methods, also methods for discriminating between competing models. And the procedure you can use now in two ways. So sequential or parallel, so you need a first guess for the parameter, then you design one or even more parallel instruments, you realize the experiment, get new data, and do a parameter estimation, and with the improved values, you go into the cycle again until you're happy. And in order to show this for what we did for the industry there, I want to give you this example, the so-called urethane reaction experiment that was important for having the industry accept the new mathematical methods. You must imagine there is an experienced chemist that knows how to do experiments. And then the mathematicians come and say, well, we have a method that tells you how to perform the experiment such that at the end you have 100 times more information than with your approach. That is not easy to tolerate for an expert from the chemistry. That there is mathematics that actually can do it much, much better than him. So this experiment was very important, and so we did this together with the head of the laboratory. The main laboratory, this is the main laboratory of BASF a little over 100 years ago. It looks different today, but we had the chief expert of BASF to be our partner, and the competition was he had to make a design, and he chose to make 15 experiments at constant temperatures, but different constant temperatures, and 90 measurements. And at the end, the 8 parameters had an error, estimated error of 32% maximum, this one here, which is due to an equilibrium reaction, which is really a problem in experimental design. But BASF chose it that way. So the mathematical optimum design just needed 2 experiments, one after another, varied the temperatures, did only 32 measurements, and all parameters were with an error within 1%. So it's hard to say. These are the 2 optimal experiments. This is the first optimum experiment here. And here you see the controls, the 2 feed streams in green and blue, and that's the temperature profile. And these were the measurements that you can take at different times. The times were also optimized. And this is the second experiment, which has a completely different profile on the feed streams and on the temperature, and also completely different measurements, and of course a different path for the reactions here. But if you look at the results, then you have a much higher accuracy for your parameters, and we were able to reduce the cost, but because we only did 1/3 of the measurements, which are the costly part in here. So instead of 6,000 euros, our 2 experiments only cost 2,000 euros. That may be not much, but you do that every day and you do that very often. So BASF is now using these methods. But I should say that this expert, the head of the main lab, was also on the list of authors when we published this, and he was actually happy because we did everything together with him. So our success story here is also his success story, and now they are using it every day at BASF. And they even, in the typical words, they say that they save up to 80% with these methods and get much more precise results. And they are so proud of it that they even published it in the German newspaper, the kind of local equivalent of Nature and Science, German Bild-Zeitung, maybe some of you know this, 2008, that they would save 80% of the cost and of the time. And that was some procedure, because BASF is usually very reluctant to publish anything about improvements in their department. So you can also do that in real time, and then the idea is that while you are doing the measurements, you can re-estimate your parameters, get better estimates of the parameters, and re-optimize the experiment. And we did this here for the same problem. And you see then, if you use the data online to re-optimize the experiment, you can also be done with only 1 experiment and only 20 measurements, and it saves you even another 4 days. Instead of 6.5 days for these 2 experiments, you only need 2.5 days. And save additional 30% of the cost for the experimental analysis. So, but not always one experiment after the other is sufficient. Sometimes, as in the Candida antarctica, the Novozymes, the enzyme experiment, this doesn't work. So if you do 1 experiment, you can't get the parameters. You do 3 experiments at the same, optimize them, doesn't work. 2, 3, even with 4 simultaneous experiments which are optimized, you can't get the parameters. Only when you do 5 simultaneously optimized experiments, then finally you get some reasonable results that you can actually use in practice, and they determine total half-life and total turnover up to about 10%, which is satisfactory for the case. And Degussa was so happy to actually know this now, that you have to do these simultaneously optimized experiments. Well, just a second. These are the 5 experiments, and these are the temperature profiles. And the question, of course, is why is this optimal? Is there an explanation for the optimality, the mathematical optimality in terms of chemical terms? The answer is no. This is a mathematical solution with no chemical explanation. Indeed, the optimality comes from the fact that these 5 experiments are different. But what's the optimality of the difference of 5 complementary experiments? Nobody can tell. This is just the mathematics, since it's an optimal solution. And Degussa was so happy that they actually filed a patent on these experimental procedure for enzymes. So the final example here is another example from BASF. So at BASF we now have a group of 12 scientists, 3 of which work full-time just on designing optimum experiments with mathematical methods. And one of this example that I show you is about catalytic reactions. And what we want to have is to select the optimal catalyst geometry by their heat transfer coefficient. And the problem is the following. You have a silver catalyst on aluminum supports, but they have different geometries. On these pellets here can have different shapes. And you would like, in practice, you would like to maximize the selectivity of this catalytic production process. And this is just one example where you produce ethene. You start with ethene and have the silver catalyst, and then from that you produce ethene oxide, and plus CO2 and water. And what they want to have is the pellet with the best heat transfer coefficient to avoid hotspots during the reaction, or even possibly explosions, depending on their substance. And so you have such a standard heat conduction test reactor, and you can have time-dependent heating in there. You choose your temperature between 20 and 350 centigrades, and you can have temperature gradients of over 200 centigrades. And the problem is a 2D non-stationary partial differential equation with a relatively coarse discretization of 1,000 grid points. And the controls that we have is to choose the temperature profile or the mass current density that goes through here. And 4 parameters have to be estimated: the heat conductivity and the heat capacity. And all we can measure is the boundary temperature. Yeah, sure, I'm ready in a moment. So this is some of the simulation here, and this is the optimal experimental result. So classically, they would do 4 experiments and keep the mass current density constant, but with 4 values, and had a time-dependent heating with a ramp going up to 350 degrees. The optimal design says, no, don't do this. Choose only 1 experiment, only 2.5 hours instead of 16 hours that costs. You reduce the uncertainty, the error, by a factor of 2, and you vary the steps of G, but you have a stationary heating. So change G in 3 steps, time dependent, but have stationary heating at highest temperature. And the result was kind of surprising, because now we have a much higher and a different solution, and it meant that the company designed a completely different plant with a completely different use of pellets. And they say the effect of this is worth 10 million euros. So not only the experiments were cheaper, but the results based on the experiments made a change of 10 million euros. So this is the leverage that you can have with mathematical methods. You get better experiments, but after all, finally you do a completely different decision based on the mathematical conclusion. And that's it. And I would like to thank you for, well, first of all, I'd like to thank my partners here, our partners, for the support in the simulation and optimization group at Heidelberg. And I thank you for your patience and for your attention. Thank you.
Questions? Let's thank our speaker once again.
You're very involved with the Galileo experiment.
Pardon? No. Well, I hope that they were. I was on my way to Moscow, and
no software of yours were involved.
I hope that they are using our software, to actually determine the orbit in which the satellites are now. But since these are not geostationary satellites, I'm not sure how much fuel they actually have on board. For minor corrections, yes, but whether that's sufficient in order to get them back into the 23,000 apogee orbit that I think is still under discussion. So using our software, they should have had the answer where the satellites are exactly after half an hour, which would not have been the case with the old methods that they have been using.
Вадим Юрьевич, у вас флешка или вы хотите со своим компом?
Человеку дал, он сказал, что он придет.
Опаньки, а которому? Из оргкомитета?
Да, из оргкомитета.
Не помните имя, фамилию?
Вот.
Все понял. Хорошо. Алексей, вы сейчас поставите флешку Вадима Юрьевича.
Можно вот с той стороны свет включить, или будет сильно мешать?
Я боюсь, что он симметрично так включается. Просто смотрите, может быть, немножко плохо будет видно тогда, что на экране. Если хотите, попробуйте.
Ну давайте попробуем.
Нет, это сейчас да, включу.
Нет, сейчас доклад.
Мы цветаемся. Лучше.
Я только не знаю. В Париже среди сентября.
Сейчас опять все передвинули. Там программа 17
значительную часть мы
Просто приезжайте.
да, ну,
не каждый день.
Ну, влево.
Да, все правильно. Вот тут, короче.
Okay? Our next talk this session is by Vadim Kaloshin. The title of the talk was Periodic Hypothesis and Knowledge Diffusion in Dimension 3 and IM. Please.
Thank you. I'd like to thank the organizers for the opportunity to talk here. I will be talking about a fairly old problem, which was part of it was originated in Moscow, and the problem was posed by Arnold. And most of the work related to this work, considerable part of the work related to this talk is done jointly with Kezan, who is a professor at Toronto. So I will divide talk into 3 parts. So the first part, I will describe you a class of systems, a class of differential equations that I would like to study, and I will tell you about the main result. And the first part will also include the classes of systems which I'd like to study and main results. And in the second part, you will see example of the phenomena which I'm discussing in the solar system. And if you get lost in some formulas, which I will write down, even though I try to minimize them, then maybe in the middle of the talk you will see example in the solar system, instabilities in the solar system, which is highly illuminating example of this phenomenon of Arnold diffusion. And then in the third part, I'll tell you about some ideas from the proof and try to describe those ideas in a non-technical manner. So introduction, example in the solar system, and something about the proof. So I'd like to study Hamiltonian systems, and for simplicity you could think that I'm studying a Hamiltonian function on R2n, and there is some additional structure for R2n, for example Rn times Rn, and I would like to study equations of motion which were introduced by Hamilton, and I would like to understand properties of the solution to this differential equation. In the case when Hamiltonian is periodic with respect to Q variable, if H is Q periodic, then we could think of this equation, then star is defined formally speaking on a cotangent bundle of n-dimensional torus, but you could well think about it as something which is defined by on Rn cross Tn. And the famous question, which is ergodic hypothesis, asks the following question. So it turns out that this equation preserves energy, which means that if I consider all points PQ such that energy of PQ is fixed, then this is an invariant surface. And if I study dynamics on the dynamics, then I have to study dynamics on each energy surface separately because they are invariant. And in all times it is believed that when you're considering a typical differential equation on the energy surface, then things should be ergodic. If you want a kind of a naive definition of ergodicity, basically orbits go more or less everywhere on the energy surface. And this was a belief until the mid of the 20th century, when Fermi, Pasta, and Ulam made the following experiment. They consider a chain of particles on a line, and what they did, they wrote differential equation which these particles have to satisfy. And if you assume that your springs are ideal, then the equations are easy to solve. But if you add some nonlinear effects, then there is no analytic solution. So what they did, they tried to investigate the process when your springs are a little bit nonlinear numerically. And there was a big surprise that most of the solutions which they saw, they were almost periodic. So I don't want to write a formula, but basically they considered 32 sprints and 64 sprints, and they wrote down ordinary differential equation. In one case it was 64-dimensional differential equation. In another case it was 128-dimensional differential equation. And imagining that most of the solutions will be almost periodic was quite a shock, because when you consider an orbit of very large dimensional differential equation, then it's very hard to expect that it will be almost periodic, because there is so much space. And later, the conceptual explanation to this phenomenon was done by KEM theory. So it turns out that there are some classes of differential equations. Moreover, these classes have this Hamiltonian structure, for which it is indeed true that if you pick more or less a random initial condition and start integrating it, then solutions are going to be almost periodic. And this led to some simplification of this hypothesis. Namely, they stopped asking for ergodicity, they just asked about having a dense orbit on the energy surface, and this was a question of Birkhoff and Ehrenfest. And later I'll try to add more details, but in a very simple-minded terms, you could think of the following situation. So you have 2n-1 dimensional manifold, which is energy surface. And inside of this 2n-1 dimensional manifold, let's stick to n equal to 2. When you have n equal to 2, you have 5-dimensional manifold. And it turns out that KEM theory shows that inside of this 5-dimensional manifold there are a lot of 2-dimensional invariant tori. And you see it as a picture of them over there. And there are so many of these invariant tori that they occupy 99% of the phase space in terms of the measure. So you could think that there are these invariant tubes, and on each of those invariant tubes, trajectories are locked. And so basically, you could try your imagination. So in 5-dimensional space, there are 2-dimensional tori, but 2-dimensional tori, they don't separate the phase space, but there are quite a few of them. And the problem which arises is try to find an orbit which would slalom among those tori and try to penetrate everywhere in the energy surface. So at the moment, I don't think there is any hope of studying any Hamiltonian system, or at least large classes of, or at least generic Hamiltonian systems. So what I would like to do, I would like to restrict myself to a class of so-called integrable Hamiltonians. So if you Google integrable Hamiltonians, you will get over 20 classes of Hamiltonian systems. So I'll just write down, I'll just show you a definition of a Hamiltonian system. If you didn't see it before, then basically you could give us a definition, the following fact. So it turns out that there are, for integrable Hamiltonian systems, there are so-called action angle coordinates. And action angle coordinates, it's when you, this very implicit looking differential equation can rewrite in the following form. And this form is just very, very nice, and let me explain you why. So you hypermap from U into R. So you see you have a differential equation where half of the variables, I belongs to Rn, are just fixed. If velocity of a variable is fixed, then it's not changing. And then if I component, which is usually called action, is fixed, then this component is fixed. And it turns out that you see that half of your components are not changing, and the other half, which are called angles, are changing with constant velocity. And certainly one could solve this differential equation, and if you manage to absorb the definitions which I state at the beginning of the slide, try to read them. If not, then just think that the systems which I'm studying are systems which can be written in this nice coordinate system, where second component is not changing, and the first component is changing with constant velocity. And let me just show you classes of Hamiltonian systems for which this system of coordinates is possible. And the fact that this coordinate system exists is usually called Arnold-Liouville theorem. So I'll be just showing you examples for which, yes, such a coordinate system exists, and it's not for you to remember all these examples, but it's just to be aware that there are classes of Hamiltonian systems for which this coordinate system exists. So it turns out that all the systems from this list, they can be written in action angle coordinates. And there are, for example, children toys, which you spin depending on the symmetry. It's either Lagrange top or Kovalevskaya top or Euler top. There is a beautiful example which is called Toda lattice. So it turns out that if springs have a very particular nonlinearity, then the system is also integrable. Then there is Calagera-Moser chain of harmonic oscillators, geodesic flows on n-dimensional ellipsoid, geodesic flows of surfaces of revolution. So, I mean, nowadays there are deep technologies of trying to let me call it, integrate some Hamiltonian systems. But as I said, the only purpose of this is to say it's not that we know 1, 2, or 3, or 4 classes of those systems. There are many. And again, the main feature of these systems is that all of them can be written in that particular coordinate system where solutions are explicit. So even though all these systems are nice, but for all these systems, things should be perfect to be integrable. Namely, the potential has to be exactly this form, or potential interaction has to be exactly this form. And it seems like a very natural question is to say, okay, suppose the things are not as ideal as we think, and suppose there exists some perturbation to our Hamiltonian. Namely, let me assume that it's not that I have this idealistic Hamiltonian, but I have some perturbations of it. And let me, for convenience, I consider time periodic perturbation, but there are results for autonomous perturbation. So this is a kind of impurities. It could be impurities for springs, it could be slightly different potential of interaction for mechanical systems. And after you make this correction, then these corrections make a change of your differential equation, and this is the change to your differential equations that you have. And the main feature of the perturbed model, which is, as I said, a small perturbation of the idealistic one, is that now the action variable is no longer constant, even though the maximal velocity is epsilon. And so what one wants to prove? One wants to prove that there exists an orbit which makes a change of order of 1. Namely, with a velocity of order of epsilon, it could accumulate a change of order of 1. So our goal will be the following one. So there is a there is an angle variable theta, and then there exists an action variable. And for simplicity, for further purposes, I'll draw it as a square. This is where the action variable takes place. So what I would like to do, I would like to construct an orbit which make a change of order of 1. So that was a conjecture by Arnold. And there is a somewhat stronger conjecture which we also managed to solve. The somewhat stronger conjecture says, let me give you two open sets U and V. Then a stronger conjecture says there exists an orbit which could go from any one open set to any other open set. Okay, so let me first tell you what is the difficulty in trying to prove this result. And I will also comment on KM theory, which is a major abstraction. So it turns out that if you are trying your luck at random and you throw in an initial condition at random, then you'll have a really bad luck, because roughly speaking 99% of initial conditions to this differential equation are just quasi-periodic, and they are localized inside of those tori, and you cannot expect to find diffusing orbits using random choice of initial conditions. So let me maybe show you one example. So I want to consider the case n equal to 1, even though I'm lying a little bit, but let me choose, sorry, this is I. This is I. So let me choose Hamiltonian, the most standard one, I squared over 2. And let me choose a potential which is just a sine function. And then if you do numerics, then you see that there is quite a bit of order for this differential equation. So when epsilon is equal to 0, so phi is a horizontal variable, I is a vertical variable. So even if epsilon is equal to 0, then for the I variable should be constant, and all the orbits have to be localized in some horizontal slices. So it turns out that when you add a little bit of epsilon, then most horizontal slices will survive. I don't know if it's visible. These holes are fairly little, and the smaller epsilon, the smaller are the holes. So basically it's kind of a collection of chipses that you put on top of each other, and there are some holes in between. So this is a picture which you could see in one-dimensional case, but it turns out that that's a picture in multi-dimensional case. So in multi-dimensional case, the slices are going to have half of the dimension of the phase space, and it will be a collection of this tori. So in the picture which I showed at the beginning. So basically, in some large dimensional space, you'll have this tubes where trajectories are localized, and you want to avoid those tubes. So let me now show you. So basically, here's the main result, which is due to Arnold, Kolmogorov, and Moser. So the main result is the following. For simplicity, I would like to consider H0 of I to be sum of ij squared over 2, standard Hamiltonian. And then what I want to do, I want to define so-called Diophantine numbers. And I want to bring some meaning to Diophantine numbers. So basically, a number is Diophantine if it's not well approximable by rational numbers. And let me concentrate at the case n equal to 2. Then what I would like to say is that my condition of being Diophantine is violated if I consider some plane, rational plane, for example, plane I2 equal to 0 or plane I1 equal to 0, and I consider some small neighborhoods of these planes. And I want to consider not only one or two planes, but I hope it's visible that actually this is a hyperplane in a multi-dimensional case. So there will be many planes, there will be countably many rational planes, but if you count the volume of this of these planes, then the volume is going to be very small. And it turns out that away from those planes, namely for numbers which are away from small neighborhoods of all rational planes, motions are going to be quasi-periodic. I mean, it's hard to draw the corresponding picture, but in the rough terms, the gray area is open and dense, but the complement has measure 1 minus square root of epsilon. So most of the solutions are going to be quasi-periodic, and now you could see what will be our goal. Our goal will be to try to find orbits which diffuse inside of these channels, instability channels. So what we are going to do, we are going to find some orbits, diffusing orbits, which will be traveling inside of this violation of KEM theory. So that's our goal, and here's some more, maybe I'll just repeat the picture which you saw in the two-dimensional case. So in the two-dimensional case, I told you that most of these solutions are quasi-periodic, and there are some holes. So these holes in here, they correspond to instability channels, but in multi-dimensional cases, there are holes kind of along each direction. For example, this hole over here corresponds to the center. So heuristic picture is that in terms of measure, you need to be careful, but what you want to do, you want to stay close to rational planes, or maybe rational planes of low order. And here's the first main result. A major assumption that we use is that our Hamiltonian has to be convex, and at the moment we don't see our technology works in non-convex situation. So what does it mean convex? It means that you form a Hessian of partial derivatives of H0, and this is positive definite. So the most elementary example of convex Hamiltonian is the sum of squares, because for sum of squares, if you consider the sequence of partial derivatives, then it's going to be the identity matrix. The main result is that now you start with a convex Hamiltonian, and what you consider a small generic perturbation of your convex Hamiltonian, and then it turns out that there exists an orbit which is almost dense in the whole phase space. So what does it mean? It means that you give some precision gamma, and then there will be an orbit which covers your phase space gamma density. So if, for example, computer precision is gamma, then the orbit is going to be just dense everywhere. So in the case n equal to 2, 2 years ago with Skirzan, we finished writing a proof and gave some lectures about it. So there exists an announcement by John Mather also about the case n equal to 2, and there is a recent reprint of Chin-Chun Chen. So for n equal to 3, we posted a preprint about half a year ago, and we have almost ready a preprint in arbitrary dimension, but in arbitrary dimension we have only partial result. Namely, we realized only part of the program for n equal to 2. So at the moment you could say that we claim the result for n equal to 2 and 3 and made considerable progress in any dimension. So even though this result solves a strong form of Arnold diffusion, and a strong form means that it's not only that you could go from one open set to another open set, but you could go practically anywhere. However, there is a major difference of trying to go along finitely many channels like this or along infinitely many. And jointly with Marcel Guardia, we improved this result, and what we managed to prove that these orbits, they could go to some Diophantine KEM tori. So we managed to show that our diffusion orbits penetrate at an arbitrary small scale, and that they accumulate to KEM tori, which are highly irrational. So the major difference with the previous result is that first we are studying the case n equal to 2. Second, our orbit feels a set of positive measure, and feeling a set of positive measure is much stronger than constructing an orbit which is say 0.01 dense. Unfortunately, we could construct an orbit whose closure has 99% of the phase space, but we cannot construct an orbit which fills all of the phase space. So it's, in a sense, you could say that this is a weak form of Arnold diffusion. So there are, first result says that there are orbits which travel along finitely many resonant channel, and this one says that you could accumulate to KEM tori. Okay, so I hope that most of you got lost in the statement of all those results. So let me just show you example in a solar system where you could actually see the diffusion. So one of the examples of integrable system was Newtonian two-body problem, or sometimes it's called Kepler problem. So let me just look at the probably the most famous example of nearly integrable system, which is a solar system. So why it is nearly integrable? So in the solar system there is a sun, and sun is just so much bigger than all the other planets. Then to the first order, each of the planets, for example, Jupiter or Mars or Earth, all of these planets have elliptic orbits to the first precision, and this is what two-body problem tells us. So basically, solar system can be written in this form, where the major part of the Hamiltonian comes from interaction of planets with the sun, and other interactions are of smaller order. And it's been a fascinating, important problem to try to find chaos in the solar system. And in the 60s and then in the 90s, first people managed to find order in the solar system, namely they managed to find quasi-periodic motions which have positive measures. This is a result of Arnold, Hermann, and Fejos. But I will be interested on the opposite side. I will be interested in trying to find unstable motions. And here's a picture which astronomers did. So on the left, what you see a snapshot of a solar system, and this white sea is the so-called asteroid belt. And what I would like to do, I would like to investigate dynamics of points in the asteroid belt. And the way I want to, there are about 1.7 million asteroids in the asteroid belt. And the way I want to think about each asteroid, I want to think about it as an initial condition of this ordinary differential equation. So imagine that I have, say, 2 million initial conditions of this ordinary differential equation, and I want to see how those solutions behave. And since there are so many asteroids, 2 million of asteroids, maybe we want to kind of sort those initial conditions out according to some principle. And here's a diagram where we sort out this asteroids according to the period. So semi-major axis is the size of the orbital ellipse, or you could say that period of asteroids increases monotonically in this direction. Then you take this 1.7 million asteroids, and for each little window for the period, you count how many asteroids are there. And that's what astronomers did, and what they found out is that if you look at the distribution of asteroids, where along the one axis is a period, along the other axis is the number of them, then you clearly see that there are deep gaps. The deepest gap is when period of asteroid is 3 times smaller than period of Jupiter. Then another gap is when period of asteroid is exactly 40% of period of Jupiter, and so on. And one of the big achievements in astronomy done by Jack Wisdom is that he managed to write down some numerical experiments, and what they saw, he saw diffusion, and more mathematically he saw that eccentricity of the corresponding planets behave stochastically. And the reason you have a gap here is because eccentricity had a stochastic behavior, and this stochastic behavior led to the following phenomenon of either nearly collision or an ejection or collision with Mars. So the realistic picture is the following. This is a picture, orbit of a Jupiter. That's an orbit of Mars. And if you draw an orbit of asteroid as circular, then it will be approximately of this shape. But then as eccentricity of the orbit of asteroid is changing, then the shape of the orbit of asteroid is changing. So it turns out that if eccentricity of asteroid make changes, and if you plot here's the time axis and here's eccentricity, then there exists some critical eccentricity, approximately 3/8, such that if your asteroid hits 3/8, then it will hit an orbit of Mars, and the Mars will kick it out. So basically the explanation for these gaps is Arnold diffusion, and eccentricity turns out to be one of action variables of this problem. So if there were no Jupiter, then eccentricity would be constant in time, but since there is a Jupiter, eccentricity makes some tiny fluctuations, and in some places these fluctuations can grow and reach some critical amount. So at the moment we still don't understand very much the structure of these instabilities, but we do know that they exist. Again, one way to think about this diagram is that you take 2 million initial conditions, and then you see at the places where those initial conditions exhibit instabilities, and instabilities are in some places where periods are in rational relation, or you could think that when periods are in rational relation, you are inside of one of those instability channels or rational lines. So that's an example, and so now what I would like to do, I would like to say some words about the proof of this theorem. It's fairly difficult to talk about the proof to non-experts, but I'll try to make some analogies, and hopefully at least the very basic ideas of the mechanism will be clear. But before I'll talk about the proof, let me tell you about a conjecture which seems to be quite illuminating, recently we obtained some partial result about this conjecture. So what we would like to understand, we would like to understand the stochastic nature of those instabilities. As I said, fluctuations of eccentricity behave in a somewhat random way. And what we want to do, we want to prove some theorems about stochastic behavior of those initial conditions. And a naive way to do it is you start with some nearly integrable system. If you could absorb that this is a rotor times pendulum, fine. If not, then there is some integrable system plus a perturbation. And what we want to do more or less the same thing as we did with asteroids. We want to throw 1 million of initial conditions, and we want to integrate. And then the conjecture is that when you integrate, then you will see some diffusion process in the sense of probability theory. In other words, for example, for this case, in the vertical direction, the trajectories will be spreading out as a diffusion process. And as I said, we recently obtained some result in this direction. So we proved that there are instabilities, but numerically it is believed that there are a lot of instabilities inside of these resonant lines. So if you are inside of these resonant lines, then there will be many unstable orbits. It's just we cannot prove it at the moment. Okay, so now let me tell you a little bit about the mechanism of the proof. And maybe I'll start with some general remarks. So if you want to prove instabilities, then you have to deal with a multi-dimensional differential equation. And it's quite difficult to control solutions of a multi-dimensional differential equation. So what people usually do, they say, okay, we don't know how most of the solutions of these differential equations behave, so let us try to find some periodic orbits. And this usually is the first step, trying to understand the dynamics. And then there was a big activity where people, it was initiated by Ricardo Magnier, people were trying to find a lot of periodic orbits. And the idea was, or the hope was, that you find one periodic orbit here, then you find another periodic orbit nearby, then you find another periodic nearby, then another periodic orbit nearby. And imagine for a second that somehow we managed to prove that there exists an orbit which jumps from one periodic orbit to the next one. So, I mean, a very naive mental image is that suppose this is one of your periodic orbits and that's another periodic orbit, and what you can do, you could jump from one periodic orbit to another, and then suppose here there is another periodic orbit, you could make another jump. So the hope was that you could keep jumping from one periodic orbit to the next one, and little jumps will lead to a big increment. And so at the moment, this idea is still in the process of elaboration. I guess the main difficulty is that when you are in multidimensional space, it's very difficult to find so many periodic orbits that they are, in a sense, dense. But again, the idea is you find one periodic orbit, you know the solution of your differential equation there, then you find another periodic solution, and you are hoping to find those periodic orbits close to each other. So since this idea didn't work historically, there was even a more involved idea by Arnold. So what Arnold proposed, he proposed to find not periodic orbits, but he was proposing to find quasi-periodic orbits. And these quasi-periodic orbits, they were supposed to fill a toroid. So you could think of a periodic orbit as a circle in your phase space, and you could think of a quasi-periodic orbit as something which fills a two-dimensional torus, or fills a tube. So Arnold proposed to try to find those tubes, two-dimensional tori, which are filled with quasi-periodic orbits, and tried to organize the same process. So you are trying to find an orbit which jumps from one tube to nearby tube, and then maybe to the third tube, and then maybe to the fourth tube. So again, kind of some navigation process of jumping from one invariant set to the next one. And unfortunately, there is too much chaos, so there is too much of a swamp in instability channels. And at the moment, we don't know whether one could construct periodic orbits which jump from one of those tori to some other tori. But then you could try your imagination. I mean, maybe you cannot jump from a periodic orbit to a nearby periodic orbit, and you cannot jump from a quasi-periodic orbit to another quasi-periodic orbit. Maybe you can construct a counter set, and maybe you can construct orbits which jump from one counter set to another counter set. Even constructing those counter sets is not an easy procedure, but there was a breakthrough which started with Abri and Mather. Abri is a physicist, Mather is a mathematician, and there were technologies which are now called variational methods for Hamiltonian systems in a weak KAM theory. So those methods were well developed. However, those methods could work if these counter sets are sufficiently simple. And unfortunately, in multidimensional setting, these invariant counter sets could be quite complicated, and one cannot. So this technology had a roadblock which people had to overcome. So the main contribution, which I think our main contribution is that we managed to construct a dimension reduction. So we managed to say, okay, we don't know how to study dynamics of a multidimensional differential equation, so let's try to find invariant submanifolds. So in the very simplest setting, our phase space is 5-dimensional, and in this 5-dimensional space, we want to say something about solutions of this differential equation. So what we managed to do, we managed to find 2-dimensional invariant tubes in the phase space. And roughly speaking, you could think that we reduced our problem not to the analysis of 5-dimensional differential equation, but to the analysis of a 2-dimensional invariant submanifold. So if we construct enough many invariant 2-dimensional submanifolds, then we feel pretty happy, because then we could analyze the dynamic inside of those 2-dimensional manifolds. And let me mention the subclass of systems, namely 2-dimensional maps. And it turns out for these 2-dimensional maps, there is a lot of structure which can be analyzed, so maybe I'll just give an example of a 2-dimensional map and tell you. So these 2-dimensional maps of a cylinder, you could think that they are subsystems of this differential equation. So what we analyzed, for example, I gave it at the beginning, so phi plus I plus epsilon sine phi, I plus epsilon sine phi. So phi is a variable in the circle. Maybe I should put 2 pi here and 2 pi here. And I is a variable on R. So this is a map which is very easy to plot. This is the direction phi. This is the direction I. So it turns out that you might have an epsilon here, or you don't need to have an epsilon here. So there is a class of systems which are so-called twist maps. So there are some large classes of maps of a cylinder, such that there are a lot of invariant sets for those maps. So as you can see, there is not that much of an order. If you look at these maps first, there are some stochastic region where things behave in an unpredictable way. Then here there is a little bit of more order. But basically what Mather and Abri proved, they first constructed periodic orbits. For example, this is a periodic orbit of period 2. Then they managed to construct periodic orbits of period 3. And then if you start looking at these pictures, then for all periods, they managed to construct periodic orbits. But not only they managed to construct periodic orbits, they managed to construct some Cantor sets. So this white-green is a Cantor set. Basically for all so-called rotation numbers, so you could say a frequency, namely average speed of rotation around the cylinder, they managed to construct invariant orbits, what they managed to do, they managed to construct orbits which kind of navigate through this chaos and, for example, go from the bottom to the top, more exactly, and that is already a work of Mather, they managed to construct orbits which could jump, say, from green to red, then from another green to red, to green, to red, to green. So they managed to construct orbits which diffuse in the same way as... how much time was left? So actually, no, let me go just to the end. Maybe I'll show to a shape. So, okay, basically, if you could deal with invariant cylinders, if you could construct invariant cylinders, then roughly speaking, there were technologies to construct diffusion orbits. But maybe one last thing which I could tell you, and you could understand it without technical difficulties, is that I told you that there are invariant cylinders in my phase space, or in the space of differential equations. And it turns out that these cylinders, they have a very strange shape. Namely, they are like these IKEA lamps. So you take an IKEA lamp, and some of them have a design that they are kind of squashed. And these IKEA lamps, I mean, they are, as a matter of fact, they are very long, but since they are squashed, they have this wrapped or crumpled shape. And it turns out that these cylinders, they, at a distance of order square root of epsilon, they have those folds which are kind of fancy. So maybe what I want to say is that when you take this differential equation and try to find an invariant two-dimensional submanifold to invariant cylinder, then these cylinders have a very strange shape, namely they are crumpled in the vertical direction. So they are kind of IKEA lamps. And I guess I'll stop here.
Question, please. Yes.
You mentioned before that it was tried to have a sequence of periodic orbits, and then you said, and then jump from one to the other. What do you mean by that?
Heteroclinic orbits.
Constructing orbits, it's not in the sense of probability.
No.
Because you also had stochastic, because sometimes one also has a certain probability to go from one to the other.
So what I meant is one needs to construct transition chain. So
you really want orbits? Yeah. Okay. As you did in the last mentioned, finally you said that is construction of, because you also were talking about randomness by perturbations from the, as you said.
At the moment we are developing probabilistic tools which would not use invariant sets.
But if you have some stochasticity in it, then you could maybe come from that with a certain probability. You may move from one neighborhood to the others.
Right. So if you have stochasticity, it becomes not a classical problem. And yes, there were studies about that. We are studying deterministic differential equation.
But we know such approach in other situations of Hamiltonian systems where you can do that.
Yeah, with randomness. Right?
With randomness.
Yeah, I don't want randomness.
Okay, I have such a comment. Okay, let me speak about autonomous systems. So the following picture is very familiar for us, that if we have 2 degrees of freedom, then we have, two-dimensional tori that divide the 3-dimensional energy level surface, and so for 2 degrees of freedom, we have no Arnold diffusion, we have false quasi-ergodic hypothesis, but for more than 2 degrees of freedom, these things appear. But all this is true only when we have systems that are close to Liouville integrable systems with conventional symplectic form and so on. So if we have Hamiltonian systems with exotic symplectic form, with non-exact symplectic form, then it is possible to create such a picture for an arbitrary number of degrees of freedom. So we have, for example, n degrees of freedom, arbitrary n, and it is possible to create invariant tori of dimension 2n minus 2 that divide the energy level surface of dimension 2n minus 1 in exactly the same way as in the conventional case for 2 degrees of freedom. And so for such exotic case, we will have no Arnold diffusion and false quasi-ergodic hypothesis for an arbitrary number of degrees of freedom, however large it is.
I mean, if you change the problem, you could have a different answer.
Yes, of course. Okay. Thank you.
Technical question. In your formulation, you assume that unperturbed Hamiltonian is strictly convex. Yes? You also, the question, is it so important? Some small remark. You also mentioned Cheng, and then Yu, and then Zheng, and so on. Yes? They also managed to study Arnold diffusion. And they use the theorem of Cheng from 96 about the existence of a parabolic tori for any convex. There is no relation. But why convexity is so important?
Convexity is so important because for convex systems, there is a solution to minimization problem. So if you want to go from one point to another point with minimal action, then solution which minimizes action always exists. And this leads to a large class of invariant sets. If you remove convexity, there are a lot of counterexamples. So there is no, there are no variational methods in the sense for every variational problem within a large class there exists a solution. That's a main insight.
Okay. But the mother theory is on the other language. It is theory of very weak or measure-valued solution of Hamilton-Jacobi equations.
Right. So
it is correct because, for example, one of the example of the theory, it is Federer theory of flows, something like this in geometry. Because it is very general measure-valued in this framework. Convexity, for example, is not so important, only some increasing on infinity.
Okay, so there is a work of Popov, Nicolau, Leonce, and Varadan where they constructed solutions for Hamilton-Jacobi equations.
Evans also.
And then Fatih showed that these solutions in the convex setting correspond to invariant sets, many invariant sets of the Hamiltonian system.
Yes.
And he proved that these invariant sets are exactly the invariant sets which Mather found. So for convex Hamiltonians, there is a deep connection between so-called viscosity solutions of Hamilton-Jacobi equation and invariant sets.
Therefore, there is some relation between Mather theory, because I asked Evans, who also write, he said he don't interesting Mather theory. Okay.
Depends
Thank you very
on
much.
the purpose, yeah.
Depends on the purpose. Okay? Questions no more? Thank you. And now our morning session is finished, but conference still continue to the end.
Well, we have a lunch break and we will continue at 3:30.
Yes. Right. And I'm a little confused introducing myself as a first speaker. So let us start. Well, my talk is about continuous dependence of a functional differential equation on the scaling parameter. And the situation we consider is the following. We have a functional differential equation and the boundary value problem for an elliptic one, to be precise. And there are some parameters responsible for arguments transformations. And we change these parameters and want to know whether the solution depends continuously on these parameters. Let me start with the following very simple but very useful observation. It's the abstract setting. We have a bounded domain in Rn, a fixed L2 complex function f, and we also have a family APUV, a family of continuous sesquilinear forms on the Sobolev space H01, and this family depends on the parameter and satisfies the following two conditions. The first one is continuous dependence on the parameter p in this sense. The function h p of u here is such that it tends to 0 as p approaches a fixed value p0 for any fixed u. We don't have any uniform convergence to 0 here. For any fixed u, we have a function hp satisfying the following condition. Well, for simplicity, and this is really without any loss of generality, let us consider the case of a scalar parameter ranging in some neighborhood of a fixed value p0. And while in the first condition we do not require any uniform convergence, the second condition is the uniform coerciveness condition with respect to the parameter. So we want a positive constant gamma to be independent of u and also of p. Then there exists a unique solution up to the identity, and moreover the solution approaches the solution for this fixed value p0 in the h1 norm as p goes to p0. The establishment of the unique solvability is quite standard, and we omit the proof and only touch upon continuous dependence on the parameter. This is the whole proof here. First, we can write down these two relations. the expressions on the right-hand side are the same, because f is the fixed function. Therefore, we can equate the expressions on the right-hand side. Then we can write this, and substituting the difference up minus up0 for v in the last identity and taking real parts, we get the following chain of inequalities. Here we use the second condition, uniform cohesiveness condition, and here we have we use the first condition. Let's misprint here. P0 should stand here. Okay.
What is in the center?
Hmm?
What is in the center?
Where?
Just between these inequalities, the middle inequality. This is less than the subsequent.
This one or this one?
This one.
This one?
No.
No, this one.
This one.
We estimate the real part by the absolute value, and then just write it. This is equilinear form, so we can write this as the difference. And now it follows this relation, and I just know that the function HP 0 must be here. HP 0 is calculated for the fixed solution UP0. Therefore, it goes to 0 as P goes to P0. So it's quite simple. And next, I would like to explain how it can be used in applications. In application to functional differential equations, P can be responsible for transformations of the argument. And it is supposed for closed values of P that the corresponding transformations are also closed. And then, roughly speaking, relation 1 is an easy consequence of the mean square continuity of functions from L2. So it's not a problem. And the whole matter comes down to cohesiveness condition 2. It must hold uniformly with respect to the parameter P, and we then call it the uniform cohesiveness condition, UC. And it is very important to note, and I'll stress it several times during my talk, that the fulfillment of the inequality, of this cohesiveness inequality for the fixed value P0 does not mean the uniform cohesiveness in a neighborhood of P0, no matter how small this neighborhood is. And remark, in the theory of differential and functional differential equations, inequality 2 is known also as the Gordon type inequality, and the corresponding equations are called strongly elliptic. And my first example is about differential difference equation. Let omega be a cylinder where G is a bounded domain in Rn minus 1, and we consider the following differential difference equation. R, I, J, epsilon are difference operators with constant coefficients A. They act along the axis of the cylinder, and the shifts are multiples of epsilon. And of course, the corresponding sesquilinear form, the form corresponding to the Dirichlet problem, looks as follows. And of course, I must say that for a fixed value of epsilon, this problem is a simple and very special case of problem studied by Skubachevsky. But what is new now is problem 3 is considered for all arbitrarily small values of epsilon, and we let epsilon go to 0. And for epsilon equals 0, we have a just differential equation. We formally put epsilon 0, and then we have just differential equation. Here you can see the necessary and sufficient condition for the uniform coerciveness. It looks as follows. Finite. Integers, finite. Yes. Finite set of integers. And this is not the usual symbol of a differential difference operator, since we have an independent variable eta instead of xi1 in the exponent here. And of course, you can't find epsilon in this criterion because we have already passed to the limit in some sense as epsilon goes to 0. But it is very important to know that this condition is that on the other hand, passing to the limit, we do not have we do not obtain the condition of strong ellipticity of that limit differential equation. We have something different, because you can see here this this requirement, this inequality is strong ellipticity of the limit differential equation, and this condition is of course weaker than 4. 4 is the necessary and sufficient condition for the uniform coerciveness. Well, if this condition is satisfied, then problem 3 has a unique solution for all values of epsilon small enough, and we have this continuous dependence on epsilon, where u0 is the solution to the limit Dirichlet problem for a strong elliptic differential equation. And this is an example showing that for such values of b, we have all what we need. But if this condition is violated, for example, let b be greater or equal than 1/2, then while the formula limit equation is just the Poisson equation, and we can find for a fixed epsilon, say 1/n, we must take this this matrix of order n times n and check its non-degeneracy, and this will guarantee the existence of a unique solution. But it is not easy to see what happens as n goes to infinity. So, well, it's just an open problem, even for this very simple case. But if the real part of b is less than 1/2 by absolute value, then everything is fine.
Where from this matrix arises?
A special technique has been developed to study differential difference equations. You can find it in the book by Skubachevsky. This matrix is responsible. The next example is connected with an equation with rescaling. So instead of differential difference operator, here we have contractions and expansions of the argument x, and the remaining part is similar, and so it has the similar look. And for a fixed value of q, this problem was studied before, but now we consider all the values of q greater than 1 in a neighborhood of q equal to 1, and we let Q approach 1. And for Q equal 1, we formally have the same differential equation. And the obtained necessary and sufficient condition for the uniform cohesiveness is just the same. It's quite natural from one hand, but from another hand, it is well known that the theory of this type of equations for a fixed Q greater than 1 is totally different from the corresponding theory for differential difference equations. And we can write down the following example. And now this condition 4 turns to this condition. And if this condition is violated, then it was shown before that the Dirichlet problem in this example has an infinite dimensional null space for all Q greater than 1. So we may no longer talk about continuous dependence since we have here infinite dimensional degeneracy. And the last case studied quite recently is the case where we have two different parameters. Parameter Q and the parameter P. They are absolutely independent. And we fix one of these parameters, for example, Q, and let the other one range in some segment from 1 to P0, P0 greater than 1. And our task is the same. First, we want to establish the existence of a unique generalized solution of the Dirichlet problem for all values of P close to 1. And then we want to study the behavior of the family of solutions UP as P goes to 1. Now, the formally limit equation, where P is put equal to 1, is already an equation with rescaling. Here it is. And they were obtained the following necessary and sufficient condition for the uniform cohesiveness. It looks as follows. A necessary and sufficient condition for the existence of a number P0 such that estimate 2, our principal estimate, holds on the segment. This is the following algebraic inequality. And it is very important to know that a necessary and sufficient condition for the Gordian type inequality for the limit equation, here it is, looks as here it is, looks as follows. So different from this one, it's much weaker. And the following example is shows this. Let us have this equation with two parameters, P and Q, and if A and B, let A and B be positive, and C be a complex number such that the following two inequalities be fulfilled, then this equation satisfies the Gordian type inequality only for P equal to 1, but not for P greater than 1, no matter how small the difference P minus 1 is. Just a few words about idea of the proof. We approximate P by rational powers of Q, and then the known results from paper 2 can be directly applied. So, and by the end of my talk, I would like to mention that functional differential equations with rescaling have been actively studied by many authors, by mostly in the one-dimensional case. For example, take the well-known pantograph equation. Interestingly, it arises in quite different fields of science, in astrophysics, absorption of light by interstellar matter, engineering, dynamics of contact trolley wire, biology, cell growth and division. Catte and MacLeod were the first to perform a comprehensive study of asymptotic behavior as t tends to infinity for the pantograph equation. Later on, various generalizations containing rescaling under the derivative sign were considered by many authors. Just written, just 4 of them. And for example, this boundary value problem is closely related to the damping problem arising in control theory, damping problem for control system governing by the generalized pantograph equation. So I think I finished now. Thank you very much for your attention. Since I'm also chairman, please, your questions.
If you have the scaling there, then you really take 0 as an important point. Can you have distributions?
I have several what?
Can you have distributions? You could scale not just in 0. Here you have time, but if in space it would be interesting to have different centers. Then you have a sum.
Yeah, not so far.
It cannot be. It cannot be transported.
It hasn't been studied as detailed and as this case. Thank you. What that more? This one probably.
It's not an example. The next slide is an example. Yeah. Here, the essential point in this example is that coefficients also depends on P and Q. Do you have the examples when coefficients don't depend on the parameter, and nevertheless so you have constant in parameter coefficients, yeah? And you have only scaling, yeah? And nevertheless the conditions of existence and continuous dependent differ. Here is quite essential that there is P before B in the center.
Here?
Yeah.
We just write this line for simplicity. It looks better than this one. So
maybe, but maybe I ask another way.
Here we don't have any current.
But as I see in this conference, in the talks of your colleagues, you write equations in different forms. Sometimes you first move the argument and then differentiate. Sometimes you deal vice versa. and sometimes you divide. Is this effect essential for every variable?
It is principle for me that that I differentiate.
Once.
I can differentiate once, but not twice.
Yeah.
So these two ways are possible. And of course, our solutions are only H1 solutions. Typically, they are not H2. It's a principle. So.
Thank you.
Thank you.
More questions? So if not the case, let's thank the speaker again.
Now I am pleased to introduce our second speaker, Sergey Tikhomirov. He will talk about vector fields with shadowing properties corresponding to various classes of reparametrizations. Please.
So thank you very much for the introduction. I'm happy that I'm not the organizer, so I have an opportunity to thank the organizers for organizing the conference. And so I'm going to speak about shadowing for vector fields. This is a small result in shadowing, so I do not assume that all of you knows what it is. So first I will make an introduction what shadowing is. Then I'm going to speak just about some simple result, which is now paper submitted. And I would like to thank supporting organizations which supports my research. So what is shadowing? So I'm going to speak about shadowing for vector fields, but first I would like to consider a simpler case, so shadowing for diffeomorphisms, just so you have an idea what is going on. So let M be a smooth compact manifold. I need Riemannian structure on it, and I say that I have Riemannian metric dist. So assume that I have a diffeomorphism of this manifold, and the critical notion for study in shadowing theory is notion of pseudo-trajectory. So sequence of points of manifold is called d pseudo-trajectory if image of a point is close to next one. So next point is close to image of previous one. So this means that we iterate our diffeomorphism, but on each step we make a small mistake. Yeah, so this is naturally appears, for example, if we do numerics, or if we don't know the law exactly, but we know it approximately, so we just the real situation in nature is just gives us pseudo trajectories, not exact trajectories. And the main topic of shadowing is when properties of pseudo trajectories are similar to properties of exact trajectories. So the critical notion is shadowing property, and it tells the following. So we say the diffeomorphism has shadowing property if for any epsilon there exists d such that for any d pseudo trajectory yk there exists an exact trajectory xk such that pseudo trajectory and exact trajectory are pointwise close. So informally speaking, near any pseudo trajectory there exists an exact one. So this means that if we assume that diffeomorphism has this property, then if we do numerics and see some pseudo trajectory, this means that okay, this is really reflects what is happening in the system, because nearby there is an exact trajectory as well. So it naturally appears in numerics, as I explained, but historically it first appears in the theory of structural stability. So when instead of diffeomorphism F, we consider its small perturbations and study properties of small perturbations of original, small perturbation of original diffeomorphism. And if we speak about shadowing, we need to speak about shadowing lemma, and we need to speak about hyperbolicity, so that the notion and the lemma was introduced by Dmitry Viktorovich Anosov, so who is unfortunately not with us, but his theorems are forever with us. So the critical notion is hyperbolicity. So we say that set lambda is hyperbolic if we can decompose tangent bundle. So first of all, set need to be invariant. And we need to decompose tangent bundle over this set into sum of two subspaces ES and EU. S means stable, U means unstable. And this splitting should be invariant under action of derivative of differential. And ES should be uniformly contracting, and under this I mean the following. So there exists some constant n, so number of iterations. And if we consider any vector starting in any point in the stable subspace and make n iterations with the differential, then it will be uniformly contracted. So it will be contracted in a ratio lambda, which is strictly less than 1. So, and the similar holds for unstable direction, but this means that after n iterations we expand it uniformly. So, and the special case when lambda is the whole manifold is, in that case, diffeomorphism is called Anosov diffeomorphisms, but of course, because Dmitry Viktorovich was the first person who considered them, but of course he didn't call them Anosov. So Anosov is how we call, he called it U systems. So if you see U systems, this means the same notion. So for you to have an idea what means hyperbolicity, I give an example. So let us consider map of two-dimensional torus, linear map, and so I write explicit form. And but what is important? Important that determinant is equal to 1. So this means that this linear map really generates diffeomorphism on torus. And the second important is that both eigenvalues by absolute value are not equal to 1. So this would correspond to the fact that the biggest eigenvalue would correspond to unstable direction, smaller, so the one which is smaller than 1 corresponds to stable direction. So this is the simple example. If for you definition of hyperbolicity is too complicated, you can have this in mind. And if this is complicated for you, you can think about one point whose differential have eigenvalues with absolute value not equal to 1. So in the Anosov shadowing lemma tells to us that if we have a hyperbolic set, then in a certain neighborhood of this hyperbolic set, diffeomorphism has shadowing property. This is shadowing lemma, which was done in 90s. So now I come to shadowing for vector fields, so the real topic. I will start with explaining why this problem is different with shadowing for diffeomorphisms. So let us try to repeat at least definition. So instead of diffeomorphism, we consider a vector field and corresponding flow. And notion of pseudo trajectory can be nicely repeated. So we say that map g of t, which acts from real line to the manifold, is this pseudo trajectory. If the following holds, so here is a complicated formal definition, I will give informal explanation. So let us consider any point on pseudo trajectory, so g of t, and let us consider two shifts on time tau. So one is along pseudo trajectory, and one is along the flow. So we have two different points. But we assume that if tau is small, so less than 1, then the distance between 2 points is small. So this means that during time 1 we make only small errors. So if we try naively to repeat the definition of shadowing property and say that for any d pseudo trajectory there exists an exact trajectory which pointwise shadow it, so which would be just repeating from diffeomorphisms, we will encounter a problem. Let me explain what it is. So assume that we have a closed trajectory, and for simplicity assume that it is attracting. And consider as a pseudo trajectory the motion along this closed trajectory, but slightly faster than the vector fields provides us. So in that case, if d star is small enough, then it will be a d pseudo trajectory. But the problem is that it cannot be shadowed by an exact trajectory, because exact trajectory will follow this closed trajectory with one speed, and pseudo trajectory will go with other speed, and at a certain moment they will be in opposite parts, so they cannot be close to each other. So what help us? Help us notion of reparametrization. So we say that consider reparametrization of time, and reparametrization is an arbitrary increasing homeomorphism of real line. And technically for us it's simply assume that h of 0 is equal to 0. So here, up to now, I don't assume anything except that this is an increase in homeomorphism, so it might be very fast, much faster than the original time. But I will also need somehow restrict the set of set of reparameterizations. So we will consider, for any epsilon, we'll consider reparameterization which satisfy this inequality, which means that they are close to identity. And inequality looks complicated, but if we additionally assume that it is differentiable, this means that a derivative of h is epsilon close to 1. Yeah, so we are moving not faster than 1 plus epsilon faster than than original time. And the class of this representation we call rep of epsilon. And now we can define the shadowing property, which will be a reasonable notion. So we say that diffeomorphism has shadowing property if for any epsilon there exists d, such that for any d pseudo trajectory g of t exists a point and a reparameterization such that pointwise distance between pseudo trajectory and a reparameterized exact trajectory is small. So now I make two definitions. So because they're different with the assumptions on reparameterization. So do we assume that it is close to identity or it is an arbitrary one? So and the feature is the following. So up to now there is no agreement what of those two definitions is more correct. So I call the standard shadowing and oriented because I just called them from the time when I was student and my advisor told me to call them like this. But actually if you go to works of other people, sometimes this is called normal shadowing and this is called strong shadowing. Sometimes this is called normal and this one is called weak. So there is no exact agreement. But both of them are good in a sense that if you define hyperbolicity in a similar way to diffeomorphisms, you will have shadowing property and both of them. And it's clear that what I call standard shadowing is stronger notion than oriented shadowing because here there are more assumptions on reparameterization. And so the main question which I consider in this talk is, does this notion are actually different? Because if one defines structural stability, there is also notion of reparameterization there, but it practically do not depends on restrictions on reparameterization which you make there. So the question was formally posed by Kamura in 1984, but after quite intensive investigations of different definitions of shadowing property for vector fields, which mostly made by Thomas and Kamura. And so they considered other definitions as well, but about all of them was proved that they're either not reasonable or equivalent to those two. So this is two main definitions. And it was proved that if vector fields doesn't have singularity, so don't have fixed points, that oriented shadowing and standard shadowing are equivalent. And this is easy to see because if you are far from fixed points, so you have a speed which is separated from zero, and if your reparameterization is very different from identity, then you just go very, very far away, and so you cannot be close to pseudo trajectory. So, and the main result of the talk is that, I constructed an example on a 4-dimensional manifold. 4-dimensional is important, the precise form, I believe, is not important, and which has oriented shadowing but do not have standard shadowing. This is up to now the first example of this type. So this is notions are different, and so the question which of them is more correct is still valid. So one has to decide. So and below I will briefly explain the construction of the example. So this is the manifold, 4-dimensional, so I consider vector field X. It must have, for me, it must have two singularities, two fixed points, P1 and P2. Both of them are hyperbolic. Each of them have 2-dimensional stable manifold and 2-dimensional unstable manifold. So which is, okay, schematically it's not shown there because I don't know how to draw 4-dimensional pictures. So here unstable manifold is 2-dimensional. You should understand that stable one is also 2-dimensional. Essential construction, part of construction that I assume that there exist intersection of unstable manifold of point P2 and stable manifold of point P1. So there exists trajectory, heteroclinic trajectory from P1 to P2. And because of the dimensions, it cannot be transverse. So because two-dimensional manifold, two-dimensional manifolds in four-dimensional space, if they intersect transversally, they intersect by a point. But because we are in the case of vector field, if they intersect by a point, they intersect by trajectory, so by one-dimensional object. So this intersection is not transverse, which immediately puts us into non-hyperbolic situation for, so kind of shadowing lemma cannot be applied here. And the other thing, what I assume that very special structure and unstable manifolds of point P1 and stable of point P2, so not those which intersect by but others. And so on. For this picture, it's essential so that dynamics on both of them looks like spirals, so you're spiraling along around zero. But actually I need much more, and I will explain on the next slide what much more I need. But the general feature is that because of those spiraling and because codimension of this non-transversal intersection is 1, and this is also essential, I can practically find trajectory which goes from any point from small neighborhood of any point on the unstable manifold of this point to stable manifold of this point. So any 2 points I can connect by an exact trajectory, and for this I need spirals. So, but I need much more about spirals. So this is two-dimensional, stable and unstable manifolds are two-dimensional. So let me just consider restrictions of them. So this will be special two-dimensional manifold. And let me, so special two-dimensional vector field, and let me write it in the polar coordinates in a small neighborhood of 0. So in radial coordinates, this is just standard hyperbolic expansion. So A is bigger than 0, so because of this, this will be expansion. And what is happening in angle coordinate? So I would like them to be dependent on the point, on radius, so it's not constant, and I would consider a very special function 1 divided by logarithm. And because 1 divided by logarithm is a kind of singular function, yeah, so there will be a problem. So I need to check if this vector field is smooth enough. So continuity is trivial, but smoothness one have to check. And it will be smooth vector field, but surprisingly this is C1 but not C1 plus epsilon, so there is not higher regularity. And actually below I will show two properties of this vector field, and I don't know how to construct a regular two-dimensional vector field which satisfy those two properties. First property, which is easy to check, is that if you consider arbitrary point and consider iteration backwards, so time goes to minus infinity, then it will make infinite number of loops around 0. So here is the picture of two trajectories of this vector field. The red point is 0, and this is initial point for two trajectories, and this is trajectories, by the way, for the same time. So we can see that during the same time number of loops very strongly depends from where we start. So, but because of this choice of function, we will make infinite number of loops, which would correspond to the fact that integral of 1 over t when t tends to infinity is infinity. So this is choice of this function is very sharp in a certain sense. And by the way, for this we need that function b of r is big enough, so it's separated from 0. Not separated, but we need certain inequality on it for this. And the second property is hardly stated here, so it's quite technical, but this means the following. So if we consider 2 points which are initially on the distance of epsilon, and if when we iterate them forward, and one of them we have no reparameterization, and for other we have reparameterization of order rep of epsilon, so close to identity, and they keep being nearby, so they keep being close, then this means that originally their arguments, so their angles, was close. So and here this, I write, so I need just that they're close by p divided by 4, but that they're kind of arbitrarily close. And what is telling here that there exists such epsilon that this property holds. And this means that B of R is small enough. So if B of R is big function, that this property doesn't hold. So kind of I need to choose B of R in a certain range. So it should be big enough to satisfy first property and small enough to satisfy the second one. This is quite technical, so it's, how to say, high school mathematics. Yeah, but still it takes 2-3 pages to check in the paper. So this is not so trivial notion. So I will omit the proof of this statement. And to finish, I would like to state some open questions with relation to this result and to state some discussion maybe which started from those considerations. So first of all, obvious questions. So I constructed this on the dimension, on the manifold of dimension 4. And for my constructions, it is essential. Can one do the same in dimension 3 or less? So and I have no ideas. Is it true or not? So the other question is, does there exist more smooth vector field with the same properties? And here I personally believe that the answer is true, that this is possible, but might be we need to increase the dimension of manifold just to have more freedom in other dimensions. Because this is typically what is happening in dynamical systems. So first you consider low dimensional not very smooth example, but if you want to make it smoother, quite often you can do this by increasing the dimension. And the other question is, okay, so in the definition of shadowing we had two constants, epsilon and d, and the question is how they are related. Yeah, in the case of hyperbolic systems, they're related linearly. So one can say that epsilon is proportional, d is proportional to epsilon. So is it true in this case or not? So my conjecture that actual dependence is Hölder with exponent 1/2, but this is just on the intuition, not in, I don't have good formulas for this. And an interesting feature is the following. So typically you need to decompose pseudo trajectories. So each pseudo trajectory lies either far from this heteroclinic, and in that case it lies in the hyperbolic part of our vector field, so it should be shadowed, and it should be could be shadowed, and it could be linearly shadowed. If it is close to this heteroclinic, it is also possible to shadow it with in linear manner. But this I omit this in this talk. Yeah, but it is possible. But interesting that it's not possible to shadow intermediate pseudo trajectory. So when you are not very close to heteroclinic, but not very far from it. And actually in this balance comes those estimates, but this is heuristics for me. But even simpler question is important. So is it true that they're linearly dependent? And if the answer is negative, which I expect is correct, so it's negative, then appears question which is the following. So does it imply that if we have vector fields and we have shadowing with arbitrary reparametrization, but Lipschitz dependence of between precision of pseudo trajectory and precision of shadowing, then this implies hyperbolicity. So I believe that the answer is true, because actually if we assume that reparametrization is linearly close to identity, this is already proved in my previous works, and the kind of the only situation where where I don't know how to proceed with arbitrary reparametrization was pictures of this kind. Okay, in that case I need not only this special two-dimensional vector field, but much more general two-dimensional vector field. But I believe that this special is the worst case. So in that case, if here we have negative answer, one can try to prove that arbitrary reparametrization with Lipschitz dependence between precision of pseudo trajectory and precision of shadowing implies hyperbolicity. And thank you very much for your attention.
Certainly for your talk. Please, questions or comments?
So I believe that the answer is no. So, okay, I don't have a formal theorem, but if you make those 2 points, say, coincide, yeah, and you will replace heteroclinic by homoclinic, I have a theorem that it is not possible. Okay, not exactly the theorem, it's not possible, but very good evidence to have this. And this is a joint work with Mingli and Xiaobo, which is also submitted but not published yet. But this just depends on a very complicated notions of star vector fields, and so I prefer to omit details.
Well, just a comment. I mean, there is a version of the shadowing lemma which holds in Banach spaces for C1 maps which are not diffeomorphisms. And it works even with a weakened notion of a hyperbolic set. And this is instrumental in proving certain results on chaos for some infinite-dimensional system. Now the question is, has anything been done on these things concerning oriented shadowing or standard shadowing also in this infinite-dimensional context? Banach spaces, C1 maps.
So of course something is done, yeah, and I think, so I know there are works of Pelugin where it is done, so I cannot give you exact overview, but generally speaking the maps do not give a problem, yeah, so the fact that it is not invertible do not give you a problem if you properly modify everything here. And I think when you mean a generalization of hyperbolicity, you mean something like C lambda structure. And actually, everywhere when I was speaking hyperbolicity, I meant here C lambda structure, but it's just more complicated definition, so I prefer to omit this detail. So when I speak hyperbolic, I mean structurally stable, which is for sequence of maps in Banach space corresponds to C lambda structure.
No, what I had in mind was just what you showed us in the beginning. Yeah, the definition of a hyperbolic set.
Yes.
What I just wanted to say was the shadowing lemma also holds close to a hyperbolic set, but with an even weaker notion of this hyperbolic definition of a hyperbolic set.
No, surely. This is classical. There are a lot of generalizations. One of them allows, say, to vary of dimensions of ES and EU, which is, I think, the most classical. The other one just make, how to say, instead of this hyperbolic expansion and contraction, but with topological notions.
No, but what I meant concerns the invariance properties. You can weaken the invariance properties.
Invariance.
Yeah, that's a different point.
Okay.
Anyway, thank you.
Well.
Can you explain in more detail your example system in polar coordinates? In more details, the situation when r goes to 1 and logarithm r goes to 0.
I consider this in a small neighborhood of 0. So when I go far away from 0, I just change the vector field. And actually I make it hyperbolic in that case uniformly. And so I'm interested only in a part which is close to 0. Your remark is absolutely correct. So this is only in a small neighborhood of 0. Thank you. Yeah.
More questions? If not, let us thank the speaker again. We have 5 minutes before the next talk starts.
абстрактном параметре там была какой подожди, значит, тем не менее, я все равно не помню, что решение. Это должно быть вещественно. Это. Либо ты сейчас что-то не то сказал, либо я что-то не то понял. Тогда это не называется необходимой недостаточностью. Я не способен понять, но, наверное, мне это не нужно. Ладно. Вот то место... Я верю,
Право, левый, лазерный, да. Вот это вперед, да. Вот это вперед, и лазерный указка. Вот это лазерный указка. Стрелочки вперед. Ну что, начинаем? Ой, тут тарик садится. Тарик садится. Совсем садится. Ну, ладно, сказал, когда сидит, еще пару дней работает. Микрофон у тебя есть?
Let me introduce our next speaker, Vladimir Popov from People's Friendship University. Elliptic functional differential equations with variable coefficients and degeneration. Please.
Thank you for introduction, and let me start. Elliptic differential equation with degeneration was studied by many authors. For example, I think it's a famous work is a work of academician Keldysh. It's 1951. This work was the starting point for a number of work papers, famous mathematician. In this work, Keldysh showed that for this equation, elliptic differential with degeneration, these problems may be well posed, even if one imposes no boundary condition in a part of boundary. After this work, many authors study this equation. For example, Vishek, Kudryavtsev, Fikera, Ilyin, Aleynik, Radkevich, and other many authors. Elliptic differential difference equation with degeneration was studied by Professor Skubachevsky. He considered the following problem. It was 1986 and 1997. He considered differential difference operator which can represent by composition operator L and R. Here L is a strongly elliptic differential operator and R is a non-negative difference operator. He proved that this equation can have a solution doesn't belong even Sobolev space of order 1. And interest for this equation can be explained application of these results to non-local problems arising in plasma theory. So we consider the following difference operator. We consider bounded domain Q. This is a rectangular 0 to pi times 1 to 1. And the difference operators are ij, acting in space L2, are given by the formula. This is only simple example for explanation. In general case, we can consider general difference operator with integer shifts. So in this operator, we have shifts to vector 1 plus minus. It's correspond to shift left and right, shifts by 2 and shift by 3. There are coefficient A, ij, and Cij. This is a number satisfy these conditions. Since difference operator is non-local, we have to put boundary condition not only on the boundary, but in some neighborhood of boundary. So we put the following boundary condition. U of x equals 0 if x doesn't belong our boundary Q. And we consider differential difference operator like this. Here we see coefficients bij of x. It's a smooth function which are m-periodic function. This definition I give a little bit later. And this operator acting from his domain, it's infinitely smooth function with compact support. And here difference operator which we defined earlier. So what does it mean m-periodic function? Definition is the following. Function phi belong continuous function is said to be m-periodic in closure of our boundary, our domain Q, if phi of x equal phi of x plus h. H is it's a vector of shifts. This is holds for all x and x plus h for belong closure of our domain. And M it is a additive group generated by the set of shifts. So we consider all shifts of our from our difference operator, and if this expressions is true, function is m-periodic. So we consider our domain, and Professor Skubachevsky showed that properties of difference separator can be described by properties of some matrices. I briefly explain how we can construct these matrices and how we can work with this terminology. So we have our rectangular and difference separator with the shifts. Difference separator shifts part of boundary, this part, by 1, by 2, and by 3. And the same picture we can obtain when our difference separator shifts our right part of boundary. So we obtain the following picture. Here you can see two types of subdomains. So it's the first type, or we can say first class of subdomains. It's Q11, Q12, and Q13. Two subdomains belong one class if one subdomain can be obtained by shifting 1 to vector h from difference separator. So, and the second class contains 4 subdomains. This is there are Q21, Q22, and so on. Yeah. Series of shifts. Yes, we consider group of shifts. So, okay. So we use the following matrices. For the first class, this is matrix Rij1 of order 3. It corresponds quantity of or number of subdomains in the first class. So first class contains only 3 subdomains. Therefore, matrix corresponds the first class is the matrix of order 3. So, in these matrices, diagonal elements is coefficients corresponds to term without shifts, and coefficient C, I, and these guys corresponds coefficients with shifts by 1, left and right, and this guy correspond coefficient with term with shifts by 2. And the same rule we can obtain matrix for second class. This class contains 4 subdomains, and therefore we obtain a matrix of order 4. So, and here we can see matrix from the first class, and we have additional row and column. This guy corresponds shifts by 3. So it's easy to see that this matrix is degenerate matrix, yes, and it's easy to obtain that the kernel of matrix of first class is a linear combination of vector 1, 0, minus 1. And the kernel of the matrix Rij2 is a linear combination of vectors 1, 0, minus 1, 0, and the other. So how we can see this matrix have determination equals 0. So and the next step we can formulate our condition. For this, we have to use another matrix, but in our case, our example, we can put the same notation, and we use this notation R with hat is equal R without hat. So we denote the following notation, and we can formulate the condition for our problem. Condition number 1. Back?
Return.
Yeah.
What is R star?
It's a joint matrix or operator in this. Index S is a number of class of matrix. Okay? Okay. So the first condition is a condition of ellipticity. There exist non-negative self-adjoint operators Ri such that inequality is held. There you can see matrix depends on X, but for our example we can put out it. And the coefficients, this is a variable function, m-periodic, and this is some analog of condition of ellipticity. And this inequality holds for all x of the first subdomain of class S, and for any xi. It's some non-negative differential difference operator. It can be zero, but it's not interesting for us. When it's zero, it's very trivial situation. So the second condition is a condition of degeneration. There exists some number of class S such that determination of matrix A IIS equals 0. And the last condition, it's condition of subordination of subordination of kernels of our matrices. So, for our example, we can change all these conditions, only one easier condition. These matrices are positive defined. It's for our example. And now the last notation for our main result, the following. We introduce the unbounded differential difference operator L power plus sub R acting in space L2 from his domain and defined by the formula. Here R star, it's a joint operator to Rji. So now I can formulate my main result, this theorem 1. If condition 1 holds, there exists the constant C0 greater or equal 0 and constant C1 greater 0, such that for any function u from infinite smooth function with compact support, and inequality holds. It's analog of inequality of Gordon inequality, but we cannot change this term by norm of function u in space L2, and here the same situation, because our difference operator is degenerate and we cannot change this norm. But using the next theorem, if condition 1 holds and then there exists constant C1 and C0, C1 and C2, such that for any function u and v from this set of function, inequalities hold. Using this both theorem, we can prove that our differential difference operator is sectorial, and we can construct Friedrich's extension. Also, we can study spectral properties and can prove that some theorem about theorem on smoothness solution. So that's all. Thank you very much for your attention.
Thank you, Vladimir. Are there any questions? May I ask?
Yes, exactly.
So you have your difference operators R.
Yeah.
Are they with constant coefficients or not?
Yes, our difference operator with constant condition.
And separately, you have your variable coefficients B.
Variable coefficient B, yeah.
And what if R contain variable coefficients themselves? So is it much harder?
Maybe, but I don't consider this situation.
Thank you.
Yeah.
Other questions?
We can prove that kernel is infinite dimensional of this operator. This differential difference operator has closure range, and spectrum of this differential difference operator contains eigenvalue equals 0 infinite multiplicity, and discrete spectrum contain eigenvalues lambda s.
And you have some representation by the eigenvalues too?
Pardon?
By the eigenfunctions? You can represent?
Eigenfunction?
Yeah.
No.
Okay.
I don't do it.
More questions?
Okay.
So let us thank Vladimir again. We have 5 minutes until the next talk. Да, работает все. Смотри, все очень просто. Вправо-влево, вправо. Назад, давай, да, вперед-назад. Вот, а это вот. Вот эта вот штучка, это указочка. Совпадает у всех.
I am pleased to introduce our next speaker and probably the last speaker today, Alda Tasevich from People's Friendship University. She will speak about coerciveness conditions for the functional differential equations with orthotropic contractions. Please, Alda.
Thank you. I'm very glad to participate in the 7th International Conference on Differential and Functional Differential Equations as an organizer and also as a speaker. I would like to tell you about one class of elliptic functional differential equations with orthotropic contractions and give necessary and sufficient conditions of strongly ellipticity, of its strongly ellipticity. I consider a first boundary problem in a bounded domain omega. Here operators R, I, J contains contractions and expansions of arguments. The numbers Q and P greater than 1. So here we have contraction of x1 and expansion of x2. And in this component, we have the opposite situation. The coefficients are complex constants. Function f is a complex valued function, and it is 2 times summable. So the operators P from L2 to L2, I will call them the operators of orthotropic contractions. And on this slide, I would like to give the main properties that I need to the following reasoning. So, the inverse and adjoint operators have the following form. And we see that the Fourier image of P have the same form that adjoint operator. Also, we can prove that the spectrum coincides with the circle, and before the acting of operator P on our function, we suppose that it equals 0 outside our domain. So here I would like to show you the acting of operators P and their degrees. We consider the initial domain, the ball. We see it with red boundary, and acts on it by our operators. We get some ellipses, and if we divide our initial domain by the boundaries of ellipses, we obtain subdomains, and we could organize these subdomains in classes, in the classes. So the subdomains belong to one class if we could pass the one subdomain to another by operator P. Yes. It is very important to see that the orbits have a hyperbolic structure. And our operators connect the values of function and their derivatives on the subdomains of one class. We could see also on this picture that every class have a finite number of subdomains, and we have infinite number of classes. Okay. Now I would like to obtain necessary and sufficient conditions when our equation will be strongly elliptical. Equation is called strongly elliptic in the closure of our domain if there exists positive constant C1 and non-negative constant C2, such that for all functions U finite, smooth, and having compact supports, the Gordon type inequality holds. The Gordon type inequality 3. The problem of finding algebraic analog of Gordon type inequality is called coerciveness problem, and it was solved for differential equations with non-constant coefficients and for the systems of differential equations by Wieschig and Gordon in 1951 and 1953 respectively. For differential equations, it was considered by Skubachevsky in 1986, and for function differential equations with isotropic contractions. In other words, the same contractions of for different variables. It was solved by Rosowski in 1996 and in 2012. Here we have the common notations. H1 is a Sobolev space of complex valued function that belong to L2 with their first order derivatives. And H1 with a circle is a closure of finite, infinitely differentiable functions in H1. H1 have a scalar product, has this following scalar product. What we do, we have next steps. First of all, we may prove that we could pass from the Gordon type inequality to this type inequality. So we could pose C2 equals 0. The next step is a passing to Fourier transform. We use here the Plancherel theorem, and we rewrite our inequality like this. Also, we could consider the terms with and without mixed derivatives separately. So we obtain operators R1 and R2 that correspond to R11 and R22, and we obtain the operator R corresponding R12 and R21. So now we assume that it is sufficient to prove two inequalities only on functions with supports in first quarter. So here we could see that Xi1 and Xi2 have different, may have different signs, and so we put here plus and minus. If the domain contains the region, the inequality, the Gordon type inequality is equivalent to two inequalities. Here. And now, on this slide is the main change of variables. As you can see on the picture, we have hyperbolic orbits. So now I suppose, I make the change of variables such that these hyperbolic orbits will be new coordinate lines. And we could pass to the one-dimensional operator. Here we could consider ρ as a parameter. After logarithmic change of variables, we could also obtain not the operators with contractions and expansions, but the difference operator t and t minus 1. So, and the main problem. If the domain contains the region, then the inequality, the Gordon type inequality is true if and only if we have this inequality and self-adjoint operators 6 are positively defined. Yes, and functions G1, G plus and G minus have this form. It is not easy. It is not difficult to show that the conditions 8 is sufficient for a positive definiteness of 6, and at the same time, it is easy to prove that this condition is necessary for positive definiteness of 6. But we could also prove more difficult result than if the inequality 9 is the inequality 9 holds, then the different operators 6 are positively defined. So, I'm very thankful to Professor Leonid Rosovsky for his invaluable help, and also to Professors Bernold Fiedler and Professor Stefan Lipscher from Freie University of Berlin for an idea to study this type of equations. Thank you very much.
Thank you, Alla.
I have a question. If you have, instead of 2 dimensions and this stretching and scaling down, you would have a matrix which has a hyperbolic situation. But then what would be there, I think, should work too, no? But you have conditions there. You would have directions of the eigenvalues. But what would come in the last condition? You had the products of...
last condition?
Yes, because this looks a little bit... there somehow the eigenvalues would come in of the matrix. But there, is it possible to... it should be possible to consider higher dimension. You now have R2. Contraction in 1, and but if you would have a matrix which different which stretches and scales it down in different directions, eigendirections.
You know, if they have two-dimensional case, but then they have different contractions by...
Yes, they have different. They would have different, because the eigenvalues which are contracting and expanding are different in size. But why is it? Would it then not be possible to get a result similarly? You now may have used the techniques that you are in R2.
Mm-hmm.
What do you, Leonid?
Then I of course plan to consider all types of contractions and expansions. Yes, we plan to consider the case. Then we have contractions, but different. And then there will not be a hyperbolic structure. Then our ball have image inside the ball. You know.
If you have all them contractions.
All contractions, but different contractions.
Yes, but having different contraction and expansions too. Then you had to have your situation.
Mm-hmm. But if we have not two-dimensional case, maybe three-dimensional case, two of them will be the same, so contractions, and third expansion. And maybe there will be some details that we need to consider. I don't know now how it will be. No, it's...
No. It probably is more complicated, but we have here this kind of condition, which tells you some size condition for contraction and expansions.
Mm-hmm.
But this condition is from the reduction to one dimension, in essential one-dimensional case.
Mm-hmm.
I don't think that it's possible in the situation which you suggest.
It will look different, but it should have some indication in what direction it goes, because here I have the expansion is and the contractions are multiplicatively coming in. That's why I'm a little bit...
Yes, I think it will be very interesting to find a new coordinate lines in three-dimensional case. So we use here change of variables using this hyperbolic structure and posing them like new coordinate lines. And so it will be very interesting to consider three-dimensional case. Yes. Thank you.
Thank you. Thank you. More questions? If not, let us thank Hala again. So we have, I think we have finished, because our last speaker is missing. So, the opening ceremony, the closing ceremony starts at 6 o'clock. Here, I think. А точно Вишневской не было, да? А то это самое. Саш, давай.
Смотри,
А что такое?
у нее там в одном месте был coincide the origin вместо contains, так слегка. И, кстати, тоже почему все позитивно defined, это какая-то странная.
Не,
она же еще, так сказать, при тебе бегает, да?
Ну так.
Она не самостоятельно еще.
Ну,
Человек, тут надо что-то смотреть.
Согласен.
Вот, значит, сейчас.
Так, вот, Саш, вот смотри,
Да,
это
вот,
самое.
что, вот что здесь написано?
Где?
На следующей
На
странице.
следующей, ага.
Вот что это за неравенство?
Вот это вот неравенство, вот это вот действительно фигня какая-то. Вот это был прав, и я вот тоже, значит, в спешке этот слайд готовил. И,
А что тут должно быть написано?
Сейчас скажу, значит, вместо 1 P0. Вот просто везде тупо
Не, ну,
1 замени на P0.
Хорошо.
Вот и все.
И объясни, почему это верно.
Вот это самое. Что почему верно? Вот смотри, я просто беру эту, значит, действительно часть оцениваю, модулем, вот, а дальше, значит, я беру, вот, и раскладываю, сейчас, наверное, вот поэтому.
Сейчас.
Вот, наверное, поэтому, да.
Так.
Сейчас. Да, прости, тут вот действительно единицы не должно быть никакой.
Нет, хрен с ней с единицей. Вот в этом все дело. Ты это проскочил и вот. Нет, ты объяснил, что и так ясно, что это из первого, это из второго, а вот ключевое место, что оно вот отсюда вот следует, это, потому что у тебя правые части одинаковые.
Да, правые части одинаковые.
Все, вот. Самое интересное, это в карман спрятал, я сижу и балдею. Что за Спасибо.
И когда я туда приеду, как будет конференция я напишу потому что я последние 3 года я возился с ним. Я делал я его хорошо знаю. Ну, он сейчас где-то это же шапка. Да. Почему он его подобрал? А на самом деле я его получил. В мое отсутствие я 10 лет в Ташкент не приезжал. Он подобрал его. Не знаю как. Видимо, на его семинаре выступил. И все. Думаешь, мало
Yes, I said that. No, I hope something change that. You should look at
Эндокринит, как вот я понял, это компьютер по сосудам, на совершенно не вот здесь, вот сейчас, я передокладываю. Нет, конечно. Это бывает при нарушении.
Ленечка, здравствуй, дорогой, я рад тебя видеть. И чтобы оставить хотя бы мне один бутерброд за несколько минут.
Но я совершенно не переношу. Делайте зарядку.
Мы уехали, нет, ты, конечно, мог сказать, но я на тебя не только не обижаюсь, но даже и не сердцем, потому что, во-первых, раньше 28-го все равно это самое главное, прощаться.
Хотел познакомиться, когда он вышел на пенсию, значит, вернулся в Италию, и все-таки через какое-то время 20 лет два года уже на них сделал вернулся, его не хочет его вдруг говорит, вы выдаете себя, но вам должно быть 73 года, вы выглядите. Да нет, ничего. Объясните. Зарядку из 6 упражнений. Во всяком случае, если я не спал ночью, то у меня был 12, я в январе месяц отсутствовал. Жил, правда, в другом месте, там жить невозможно, то есть из этого при соседях. Значит, я все совершенно 5-15 закончил статью, потом завел будильник в 8 утра, полтора часа спал, проснулся, естественно, я сделал эти 5 упражнений, сразу стал трезвым, чистым, как стёклышко. Пошел на экзамен. До 5 часов я и, значит, пришел домой, математику. Да там инженерная, может быть, функциональный анализ, вряд ли. Наверное, не уравнение атмосферы, все такое. Пришел домой, заметил, что там и выпил, значит, чай из колбаски, такого, так что только можно было терпеть. Я 2 чашки выпил даже больше. На мой большой и у меня семейский вот сейчас я съел и вот теперь я купил 10 видов шоколада, в котором 75% какао. Значит, белка там, это белка там 10, и есть еще углеводов мало, наверное, какао углеводов. И, значит, и пищевой волокна. Это у меня за другой, если не бывает, это бывает реально. Многие освободили. Комната в коммуналке, причем соседей нет. Они, слава богу, живут какое-то время. Я живу не у родственников, не у друзей, а одна комната за. Она спят на диване, но на раскладушке я она занимает. А потом я люблю спать на твердом. Правда, сейчас стало холодно. Холодно, потому что окно приоткрыто для кошки. И по ногам, по ногам. Это был 2001 год, когда я приехал в Турцию. 10 тысяч долларов. Это в то время. И обещали сломать через год. И до сих пор. Причем такая развалюха, что дочка говорит, можно много ставить. Там опасно жить. Все. Ее можно ставить. Лишь бы не снова помнил. Я на все свои сбережения купил, меня оказалось много, но хватило на мой Василий-Петровский. Теперь я не живу там на Белой Приморской. Но зачем? Она со мной. Нет, нужно же как-то. Нам дадут опять напомнить, больше не дадут, это точно. Мы же должны. Нет, там квартира напомнить, причем большая, 46 метров. Нам надо все-таки по отдельности, но рядом. Я не собираюсь умирать. Вот, если меня вот эта вот штука не убьет, у меня стал вес 66 килограммов. Кишечник останавливается, я живу на микроклинике. От этого зрения, потому что я очень люблю спорт. Я лечусь. Кому докажешь? Местные врачи ноль понимают. Вы представьте себе. Я был у главного гастроэнтеролога. Мой скромный, более чем 40-летний опыт показывает, что вы совершенно идиотка. Старая я никому не пойду. Я был в военном центре, меня тоже не понимал. Занял 200 тысяч, потому что там же ноль был. Ну, в Монино, там ничего не было, стены просто. Она сделала все, и даже купила холодильник с мужем. Работает. Но мне надо, чтобы это было мое владение. Тоже я, естественно. Нет, не собираюсь. Нет, вот. Много, уже пора. 80-го года, что значит уже не пора? Давно пора. Неизвестно. Я 34. Я ее отправляю, говорю, пойди в клинику тибетской медицины, там, вот где я лечился когда у меня поставили, был там абонент, и 12 метров поставил ночью, где-то 12, у меня ничего не вышло. Это было 3 октября прошлого года, защита была. Я пришел, как раз меня записал будущий доктор, у которого я абонентом был. Значит, меня это самое Чойжи-Минипаева, она меня выслушала в 40 минут до 1,5 часа. Я рассказал все от нуля. Она мне дала траву, и перед банкетом я сходил в туалет. Потом я был у них, но я нарушал диету. Я страшно люблю творог. А это холодная еда считается. И вам он очень нужен, но по 50 грамм не больше. Не больше. Забираем от него. И потом у меня же нет желтого, вот еще что-то возьмет. Потерял я. Камешек маленький был. Нет. Я ехал из Турции как раз. Нет, не из Турции. Ехал из Германии вчера. Мы с Дуру взяли билет на автобус. Надо было туда и обратно. Чтобы я уменьшил. Надо было сыр, который надо было его выкинуть, на флешке. А я и выбрал. Ну и ничего, приступ в Москву приехал. Приступ. Я отбрехался сначала. Но камешек улегся на самый выход и не ушел. Ну надо же рисовать как следует. Я же нарисовал. И вот здесь так вот боком. Здесь магазин чая.
Первый переулок это только один дом.
Это просто рядовая поликлиника. Академия наук. Ага. Поликлиника. Один, к сожалению, помер академик. Причем помер как жаропонижающий. Укололи негодяи. Негодяи укололи этот самый. Они же колят при инфарктах, они колят, как же его называют, Зрукулика. Ладно, поликлиника, он не проснулся. Как и Соболев, говорят. 86 он помоложе, и где он старше гораздо. Не помню. Да и этот был активный, Владимир Александрович. Я познакомился с ним в Польше, когда первый раз за рубежом был, и защищал докторскую. Жень, мы будем в конце представлять членов оргкомитета, или вначале кто-то скажет какие-то слова, или наоборот, мы представим членов оргкомитета? Хорошо. Dear colleagues, today is the last day of our conference. I hope it was useful and interesting for you. And now I would like to ask if somebody wants to say some words, maybe they will be useful for organizing the next conference concerning your wishes about organization of conference. And after such estimates, I'll introduce you once more all members of our organizing committee who made a lot for this conference. So now I would like to invite if anybody would like to tell us something which can be useful for next conference. Of course, we also will try to analyze all our disadvantages in organizing committee. In addition to your proposals, we have already something to write into computer memory for future. Nevertheless, I would like also to know your opinion. If somebody would like to tell something, there is microphone.
Yes, because I observed
Al, пожалуйста.
that all the staff, that was the people that not only Professor Subashevsky, but all the people that have been working with him for this conference, they are here, and there are maybe more than same order of magnitude than the participant, because it's the last day of the conference. So just I ask you first, before we go in scientific discussion, to thank them very, very warmly. I'm sorry that I said it was the first thing to say.
Thank you.
The main wish is that the conference should be.
Thank you. This is in fact great wish. We shall try to continue. Are there any other opinions? Professor Jäger, Al.
I think one of the reasons for that this is a must to continue, because we do not have very often the chance to meet on an international level from the different areas which are otherwise very split up in workshops. But here I really enjoy that we have the unity of the field too, and especially that you open it up to neighboring scientific disciplines, which is very important for all of us, but especially for the young people. I think we have to really, if you need help from the outside, you should tell us. I know how difficult it is to get the money and get the support for that. If you need this help, you should ask for participants who could, especially the foreigners, to express their opinion.
Thank you very much for your kind words and for your kind proposal. And of course, let me tell you my opinion that financial support is very, very important for us each time. I make a lot and I lose a lot of time to get money. But first of all, I'm trying to attract here first group of internationally well-known scientists. This is my, primary task. The second task is
to get money. So 1.5 years before conference, I'm writing first series of letters, and I'm inviting some of you to conference. If I, if I obtain sufficiently large number of positive answers, this doesn't mean several hundreds, no, approximately 5-10 positive answers, then I am sure that I can continue my activity with conference, and then I am trying to get money only after this. So first of all, thank you very much for coming here. I am very thankful to all participants because you are playing the main role. As for your proposal to help us, thank you very much. Also, during this conference, we have gotten great support from different organizations. We mentioned all of them here. We have got the principal financial support from DAAD via our GRISC project. We have got great financial support from RFBR, Russian Fund for Basic Research, from our university, from Academy of Sciences, and also we have obtained implicit support, moral support from International Congress of Mathematicians, but because they confirmed that we are satellite conference. This is exceptional case. For the second time, they confirmed that we are satellite conference. First time it was in 2002. It was distance of 6,000 kilometers from Congress, Beijing. Maybe it was the first case in the history of mathematics of satellite conference. And now the distance between Congress and conference is about 7,000 kilometers. So it played important role. Also, American Mathematical Society and European Mathematical Society publish information about our conference on the websites and in notices of American Math Society. Also, it was very important for us. So thank you very much. And of course, in future, we accept all your proposals concerning your help and all your proposals concerning financial support. But first of all, I'll be very grateful to you if you could recommend us some outstanding mathematicians as our invited lecturers. Now, is there somebody else who would like to propose something? Yes, please. We can give you microphone. Жень, передай. Wait a moment, we shall give you microphone.
I wish you to invite on the next conference Перельман Григорий Яковлевич.
Мы обязательно постараемся, я уже об этом... We shall try to do it, and I thought about it already, so it's a good idea. Thank you. Are there any other suggestions or comments? If not, I would like to present you members of our organizing committee. Sorry if somebody is not here at this moment. So our student Adhamova Amina. Amina, please come here. Come here, come here. She is student of applied mathematics. Which year of education? Третий курс. Спасибо. Thank you very much for your help. Bogodarov Evgeny. He is absent, sorry. Bogomazov Nikita. He is also not here. Varfolomeev Evgeny Mikhailovich. He was responsible for a website of our conference. He made pictures, as you noticed, and he typed our abstracts, our program, all our announcements. So all such topics were due to him. Thank you very much. Женя, спасибо. Веселов Антон. He is our student. Математика или прикладная математика? Pure mathematics. Второй курс. The second year of education. Галахов Евгений Игоревич. Galakov Evgeny Igorevich is working for our conferences already for many years. He is Doctor of Sciences, this is second scientific degree, and defended his thesis in Steklov Mathematical Institute. He knows 5 languages, so he helped us a lot as interpreter. He picked up our participants in the airport. More than this, the majority of letters were written by him. You know this. Thank you. Garanchuk Ольга. She is absent. Гуревич Павел Леонидович. Сюда, сюда, сюда. Сюда, сюда, сюда. Гуревич Павел Leonidovich is also Doctor of Sciences. He defended his doctoral degree in our university, and his doctoral degree was considered as the best thesis of 2008 year in the whole Russia. He is working in the group of Professor Fiedler in Berlin and partially in our department. Спасибо, Паша. Дан Диана. Третий курс. Второй НП. She is student of the second year of education, applied mathematics. She is student of applied mathematics of our faculty. Спасибо, Диана. Доровская Ксения Александровна. Доровская Ксения Alexandrovna is postgraduate student of our department, and she made a lot for booking of apartments in different hotels, and she also communicated with our TV of People's Friendship University of Russia, which made movies about conference, with newspapers and so on, concerning information of conference. Ксюша, большое тебе спасибо. Журавлев Николай Борисович. Николай Борисович Журавлев is candidate of sciences, PhD in European system. He defended PhD 7 years ago in our university. He is studying hyperbolicity of periodic solutions for functional differential equations. And in our conference, he was responsible for many other things. He picked up our participants in the airport and made a lot. I'm very, very thankful to Коля. Спасибо. Ivanova Елена Pavlovna. Ivanova Елена Pavlovna is Associate Professor of Moscow Aviation Institute. She is candidate of sciences. Also, she is my former pupil. And she was responsible for meal, for coffee breaks, for banquet and for reception, for everything. Большое спасибо, Лен. Иванюхин Алексей Викторович. Иванюхин Alexey Viktorovich is postgraduate student of Moscow Aviation Institute. He is studying aeronautics, especially optimization of orbits of satellites. I hope soon he will defend his candidate thesis. At our conference, he was responsible for all equipment, including electronic equipment, for our rooms and for the whole building in which our conference took place. Леш, спасибо тебе большое. Краснов Владимир Александрович. Вот он. Краснов Vladimir Alexandrovich is financial minister of our conference. Without him, it would be impossible to spend even 1 ruble. In fact, he made a lot because in Russia now we have great bureaucracy, and due to him we could overcome all bureaucratic obstacles and managed to buy everything, to spend money for meal, consumables, for printing our abstracts, thesis, in other words, to organize everything. He is assistant professor of our department. In September, he will defend his candidate's degree in Moscow State University in the field of topology and geometry. Спасибо, Володя. Кремнева Юлия. Какой курс? НП? Юлия Кремнева is student of our faculty, second year of education. Her specialty is pure mathematics. Большое тебе спасибо. Подожди, Юль. And today we have birthday of Yulia, so my congratulations. Спасибо. Маргарян Ашот. НП? He is student of second year of education. His specialty is applied mathematics. He made a lot for conference. Спасибо, Ашот. Muravnik Андрей Борисович. He is absent, but let me tell you a few words about him. Muravnik Андрей Борисович is also my former pupil. He is also Doctor of Sciences. Very good mathematician. He is living in other city in Voronezh, and he specially came here for 2 weeks to help us with this conference. I'm very, very thankful to him. Неверова Дарья Андреевна. Дарья Андреевна is a postgraduate student of our department. She is writing now her candidate's thesis, and I hope the next year she will finally defend. At our conference, she was responsible for registration. As you noticed, she was head of our registration, and also she was responsible for hotels. I'm very, very thankful to her, because very often she made some important decisions herself without asking me, and this helped us a lot to polish many, many situations. Thank you very much, Dasha. Pashintsev Alexander. Pashintsev Alexander is student of our faculty. His specialty is his specialty is applied mathematics, the third year of education. He helped a lot to our conference. Большое спасибо, Саша. Попов Владимир Алексеевич. Vladimir Alexeyevich is candidate of sciences. His field of investigation is elliptic differential difference equations with degeneration. He made a lot for transportation, both for airport to Moscow, and also he was responsible for buses, which connected Steklov Mathematical Institute and Hotel Узкая with our conference. I'm very, very thankful to him, and I wish him new successes. Спасибо. Леонид Ефимович Росовский. Leonid Yefimовich Rosovsky is also my former pupil, my former student. He is also Doctor of Sciences. I hope very soon he will become professor. And he is the person who is jointly with me organizing these conferences from the first conference up to this conference, without any exclusions. He helped us a lot. He was an editor of our abstracts each time, and he also made many other important things for conference. I'm very grateful to him. And once more, I would like to underline that he's working with me from the beginning. It was 1994. It was extremely difficult time. You know, maybe our conference of 1994 was the first conference in Russian mathematics after a long period of interruption in this field. Спасибо, Леня. Руденкова Юлия Сергеевна. Yulia Rudenkova is also a student of our faculty, unfortunately of different specialty, informational systems. She helped us a lot. I wish her new successes, and also to obtain at least some results in mathematics. Селицкий Антон Михайлович. Anton Mihайлович is candidate of sciences, and he was responsible for one of our auditoriums. Anton, thank you very much for your help. Смирнова Анна Игоревна. Sorry, she is absent. She is very busy, but she also she is our student from master school, and She helped us a lot, and each time when I asked her to do something, she made everything perfectly, in time, and usually a little bit earlier, with great accuracy. Tasevich Alla Lvovna. Alla was responsible for many different processes, but in particular, majority of our participants know Alla as person who was responsible for visas applications. It's very difficult task, and I don't remember even one case when something was wrong in this process. I'm very thankful to Alla. She is now our postgraduate student, and I wish her to write and defend her thesis as soon as possible. Thank you very much, Alla. Now,
and we forgot about one more our photographer, Grisha Sibala. Grigory,
yes,
please come here.
Я позвоню через несколько минут на закрытие секции, извините. This is our photographer, Grigory Sibala. You know him. He is also a student of our faculty. His specialty is applied mathematics, and I wish him new successes, and I am very thankful to him. Thank you very much. Надеюсь, ваши будете поговорить о плане. Да, я начинаю. Приходите. Now I would like to propose you to make joint picture. I hope our photographers Grigory Sibala and Evgeny Varfolomeev will help us. Жень, командуй парадом, бери микрофон. Где нам становиться, на сцене или...
We'd like to make a group photo of everybody, so please come to the scene and let's get closer together to make one big photo.
Жень, командуй сам, не стесняйся, ты командуешь. Алло, Нурсевич, извините, я только... Да. Ну, я ни о чем не договаривался. Вы хотели встретиться?